And welcome everyone to this latest edition of QNRF's Research Outcome Seminar. The theme for today's event is Advanced Materials and Processing. My name is Parakalan, Program Manager at Energy and Environment Pillar at QNRF, and my background is in Chemical Engineering and Materials. And this is the new edition in our ROS, and I'm sure you all would have attended our previous ROS, which was also online from the biomedical pillar, which was a great success, and I hope you will all enjoy this ROS event also. And before we go to the presentations, I just wanted to share that we, usually whenever we have a ROS, we have a discussion, what should be the venue, whether it is QSTP, QNCC or HBKU Student Center. I think all that can be put to rest now. We are directly into your living rooms, and so there is no excuse now. So going forward, I will be giving introductory remarks, a couple of slides to just lay the foundation for today's meeting, and then I will show you the agenda, the speakers and the titles. And then and each of the speakers will do their presentation, and you can right immediately after each presentation you'll have some time for Q&A. So please type your questions on the Q&A section of your window. Even during the presentation, if you have a question, you can type it there. Once the presentation is done, I will read out the questions to the speaker and they will respond. So we may have like 3 or 4 minutes after each of the presentation for Q&A. So I'm sure all the applicants are familiar with this picture. NPRP applicants, these are the various priority themes that you use to apply for our proposals and calls. So as you can see, energy and environment is split into energy and environment, and advanced materials is one of the key themes in the energy side. And this is a theme with high potential to generate innovation, facilitate technology transfer, and enhance competitiveness and diversification of Qatar's economy. And over the years, strong capacity has been built in Qatar research, ecosystem through various QNRF funded projects in this particular area of themes, which is the advanced materials. So I was looking at, advanced materials is like an ocean, and there's so many things on it. I was looking at the internet to find a good definition, and what you see right here is the most commonly occurring definition for advanced materials, which is materials with engineered properties created through the development of specialized processing and synthesis technology, including ceramics, high value added metals, electronic materials, composites, polymers, and biomaterials. So if you look at this, one of these famous journal, Advanced Materials, and I'm sure some of our speakers or applicants in our NPRP program have published paper in this prestigious journal. These are the keywords that they list in the journal of advanced materials. So you can see so many different keywords: energy materials, photovoltaics, metamaterials, supercapacitors, nanoparticles, carbon, fullerenes, and so on. So I hope you can appreciate that this is a very vast field of research, all under one umbrella of advanced materials. So what we try to do in today's ROS is give you a flavor of various funded projects in this particular area, QNRF funded projects, which will talk about, for example, you have aluminum composites here, and you have bioengineering applications in the bioengineering, and then you have performance electronics, which has polymers and other plastics. And then you have the applications in applications of materials in high energy and corrosive environments. And then you have solar energy materials. So as you can see, like you saw in the last slide, the proposals and the projects are touching so many different areas of advanced materials. And just a quick rundown of the agenda. So this is me here with the opening remarks, just to give you a foundation of the meeting. And then this is a very exciting talk. We have a keynote talk on the materials research in Qatar, challenges and opportunities from Dr. Hanan from the Corrosion Center. She's the Senior Research Director of the Corrosion Center at KIRI, HBKU. While curating this talk, we had a great conversation regarding various points to be discussed, and she will bring her great experience in this area to give you a very nice talk. I hope you will enjoy it. I'll start the presentation by giving a quick bio of our keynote speaker. The title is Materials Research in Qatar, Challenges and Opportunities. Dr. Hanan, Senior Research Director, Corrosion Center Director from KIRI. Dr. Hanan has 25 years of oil and gas industry experience. One of the leading experts on corrosion and materials engineering in the region. Dr. Farhat is the founder and director of the first National Corrosion Center in Qatar. The center is part of KIRI. Her resume also includes oil and gas technical service management, as well as senior inspection and lead corrosion engineering positions. She has a PhD in corrosion engineering and master's in materials and mechanical engineering from Canada. Her bachelor's degrees is again in materials and metallurgical engineering from Tripoli University, Libya. Some of my screen is blocked with the video on the side, so I apologize. I can't read the full text. She holds international certifications in corrosion and inspection. She is the chairperson of Qatar's Forum for Corrosion and Materials Engineering. Let me see if I can. Okay. Her research area of interest is in atmospheric corrosion and environmentally assisted cracking. So before I bring on Dr. Hanan to the screen with her presentation, I would like to in advance apologize if you face any technical difficulties. We did rehearsal, but as you know, with these kind of online presentations, something always comes up in the last minute and you are taken by surprise. So we try to minimize all that. But if you still face some issues, I apologize. And with that, I will welcome Dr. Hanan to come with her presentation. Thank you.
Thank you, Dr. Brekalan. Can you see my presentation?
Yes.
Okay. Okay, so good morning, everyone. Thank you to Qatar National Research Funds to give me this opportunity to talk to you today about material research in Qatar, the challenges we face and the opportunities that we will have. I would like to first introduce myself. My name is Hanan Farhat, and I'm very eager to talk to you today about my experience in material research in Qatar. I'm the Senior Research Director of the Corrosion Center, as Dr. Brekalan explains. The Corrosion Center has been established in September 2019, so we're quite new, and we're part of Qatar Environment and Energy Research Institute, KIRI, which is part of Hamad bin Khalifa University. We at KIRI focus mostly on industry-oriented research and research that has a tangible impact in the country and tangible results. So first, to start my talk, I would like to talk about material science and materials engineering. Often people mix up those or think that they are the same. They're very, very similar, but there is a slight difference between them. So material science focuses mostly on research. It looks at testing, improving products, and producing and developing new products. And it usually uses computers and lab instruments to do this. It requires material scientists to have minimum bachelor degree in chemistry or similar discipline, and they have always a strong knowledge in chemical composition. Whereas material engineering primarily focus on manufacturing everything. So you start to see materials engineering in aerospace industry, and you can see it also in simple equipment like gardening equipment. Material engineers have a minimum of bachelor degree in materials and metallurgical engineering. We often call them metallurgists, and they are more concerned into industrial production, but they're also involved in research. In Qatar, we have no program that teaches material engineering. However, we have programs that focus on material science. For example, Qatar University has a graduate degree in material science. We have quite good number of material scientists in Qatar. We have very limited number of material engineers, but we find both working together. And we see that a lot in a lot of the research that's been done in Qatar. Most of the research that I've seen was at Qatar University, coming from Center of Advanced Material, CAM. We get a lot of research from Kiri. We have a quite good group of material scientists at Kiri. Texas A&M University at Qatar also has a lot of materials research in the past few years, and it's been has a good group too. CNQ had a few materials research that's been done. Most of this research was fundamental research. We recently have seen a lot of applied research, but we still have very limited industry-based research. So one would think, why does Qatar industry need the materials research? Why would we think it's important for the industry? And so if you look at material, it's used in everywhere, in everything we use. And as a result, it's exposed to the environmental conditions in Qatar. And we all know that the environmental conditions in Qatar are very harsh. So if we look at the temperature, for example, and all of us can feel it these days in the summer, it's quite hot in Qatar. And it gets hot in most of the year. And the big problem material faces is the cycles of temperature. So the temperature is not stable hot. In the evening, you see that the temperature is pretty low, and then in the early morning hours it's low, but then we have area, especially in the summer months, where we get very, very high temperature. So if you measure the metal temperature, the metal body temperature, when you consider the radiant heat, it's around 83 degrees. That's what we measured in the field when we are in the shade. And so you can imagine that it gets very high for metals. And these cycles of temperature create a problem because the metal is then start suffering from stress due to these cycles of temperature. The other problem we have in the environmental conditions that we have in Qatar is the humidity. We have high humidity in parts of the year, especially the summer months, and mainly August and September, but we still see humidity even now in June. The humidity could reach 88%. And when we talk about humidity, we talk about wetness. And when we say that the metal surface is wet, this means that we're getting factors for corrosion. So we're getting corrosion. So atmospheric corrosion is a big issue in Qatar. It adds to it the presence of sandstorms and dust in the air that carries particles like chloride, sulfate, and when they are in connection, when they are in contact with water and the metal surface, in bingo, you got like a worst case scenario for corrosion. So that also makes the material suffer a lot in our environmental condition. So this chart is one of my favorite charts. I've used it a lot and I still like to use it because I would say this is the evidence that we got from Qatar Petroleum. And a rare occasion, Qatar Petroleum did a survey for their failures between 2002 and 2006. So they looked at all the failures that the company had, and they were looking at what caused these failures. I guess Qatar's name is missed here. So it's Qatar Petroleum chart. So when we look at it, we see that 24% of their failures are due to poor material selection. So they selected material for application they thought it would work, but it did not work. Or they got 29% of these failures due to corrosion, but that's also associated with material. Always material and corrosion work together. And so material didn't do well in terms of corrosion properties or mechanical properties. So materials' mechanical properties were not good enough for the application. We see things that are quite interesting, like welding. 6% of the failures were due to welding, 7% were due to poor design. And we see, like, for example, erosion. We see a lot of erosion, especially in the external surfaces of pipelines that are above the ground. And that's because of the sandstorms. So we see external erosion, but we also have a lot of internal erosion due to fluid. But all that says that Qatar actually needs to have a lot of work and a lot of research, material research, because of these issues. So where we are now in Qatar, most of the material science research is focused on developing new products. We see people making a new coating, developing new membranes, looking into enhancing material properties, developing heat treatment procedures. We're looking into making new products all the time. And these products are mostly tested in the labs, which makes it difficult to prove if they can actually perform well in industrial applications. So when you look at these great products that have been developed, but there was no testing that shows how they work in the real conditions or their operating conditions, makes it difficult to market these products and use. And so that's what we mostly are doing, and we should try to look at different perspective here. Field studies that we do are very, very limited. And the problem is that because of the limited access to industrial fields. Some people were lucky, you get work with Shell Qatar, for example, and they give you access to their platform, so you can put samples there and you can look at them. You could put samples in streams and you look at their corrosion or their behavior. So these are lucky researchers, but not all of us had that opportunity. So that's the problem. Some of us work on simulated field studies. So they simulate the field conditions in the lab, but it's also challenging because the real field conditions sometimes are difficult to simulate in the lab. I'm going to give an example on this. I've been working in the past, let's say 8 years, in chloride stress corrosion cracking. It's my area of interest is environmentally assisted cracking, and this is one of them. And so I've been doing this work in the lab to simulate the field conditions. And normally people, when they do chloride stress corrosion cracking, the common test we use is called slow strain rate test. And what we do in that test, you get a machine like a tensile testing machine, and you get your samples like dog bone sample. You put your sample in, you have a corrosion cell, and you put your solution around this sample, and you start, pulling your sample slowly until it fails, and you get, the crack. You get the cracking happening. So you have a chloride solution, and you start to see where your crack is happening. The problem with this test is that it's 100% failure. So you're pulling the sample to fail it. And this is not the real condition in the field. In the field, your loads, your stresses are constant. And so you have welding, you get residual stresses from welding. These are constant, they exist there. You have stresses from your manufacturing process. And so when you do the slow strain rate test, you're not actually representing the field condition. You're just using it to compare different alloys. And so I started, developing another method where I built my own test setup to have a constant load, control the temperature, so I can see what temperature would fail. So try different temperature, what temperature would cause this failure. And there was another great scientist in the UK, Dr. Alan Turnbull. He's a big name in corrosion. And he was working also with stress corrosion cracking, and the same thing, he was developing his own method, and we often meet and discuss our work. And so Alan and I were looking at, testing samples in their as received condition. We don't grind them, we don't polish them, we look at them, and then we grind and polish the samples and we do the testing. What we found both is that the results are different. When you prepare your sample in the best, nice, clean, polished surface, it's completely different than when you, use it as received condition, because cracking usually initiated with pits, and these pits occur in the surface. They are associated with your residual stresses. So when you grind and polish, sometimes you add residual stresses on the surface. So your condition is changing. And so if you look at the field, the equipment in the field, they're not ground and polished. And so the as received condition represents the exact real case in the field. But as a researcher, to publish your work, you have to have test procedure that are clear and anyone take it and repeat it and gets the same results. Otherwise, nobody will trust your results. So you got stuck into a dilemma. You know, what would I do? Would I follow the real field conditions, or would I do what I do as a researcher to have really clear, clean research steps that everybody can follow? So what we ended up doing two things: doing as received conditions and also clean surface and ground and polish. So the clean surface will tell us how to control the parameters, so we can see what parameters are impacting the cracking best, you know, more than others. But the as received condition will be the interest of the industry because they want to see how it works. And maybe modeling will combine these two together and give us prediction. We can do a prediction models that tell us where exactly this failure occur. So I'm giving this example to show you how it is that when you think that you are in the lab simulating the field condition, you might not necessarily doing that. And this is where you have to think out of the box, and this is where you want to do something that serves both your research interest and the industry. So this gets me to the point that there are very limited researchers in Qatar that have field and industrial experience. So there is a disconnection between the industry and the researchers in Qatar, because it's difficult for the researchers to see what's happening in the field. And if they're not working closely, it will be difficult for them to get results that serve this industry. And so we have very limited ties between industry, research, and academia. And that's what we need to work on. So if we look at the material research future outlook in Qatar, where we were all the time in the past is with fundamental research. So that's what we've been doing in the past. Then we started moving. QNRF came and said, if you want to have funds, you need to show that you are working with the industry. We need industry-oriented research. So that changed the perspective. So we started going for applied research. We started doing experimental development. And so we get the co-funding process, we get industrial partners, and the last stage reaching is that creating a new product. We want to have products that actually can be marketed. If you want to produce a new coating, this coating, we want it to be tested in the environmental conditions in Qatar and in the operating conditions that the industry has, so that you can prove that it works well and then you can market it. So that's where the startups, the concept of startups started in Qatar, and this is where we see it going. And this is where we think that there is a big potential for materials researchers. So are there any impactful material research opportunities in Qatar? There are so many opportunities. We get a lot of opportunities for research related to material integrity evaluation in Qatar's conditions. So metallic alloys, if you're looking at polymers, if you're looking at GREs, you know, composites, or like we're talking recently about reinforced concrete structures. So we're looking at the new bridges and tunnels, and looking at these structures and looking at their durability and their performance and corrosion of these steel bars rebars is very important to consider too. We also can look at corrosion, because corrosion is still a big issue in Qatar, either in the environmental conditions in Qatar or in the process conditions. There is another thing that we can look at is the material qualification in different process conditions. And I'll give an example of this. Recently, we're working with one of the companies that wanted to use a new corrosion inhibitors for their pipeline. So what we are looking at, we're looking into different corrosion inhibitors and testing them in the same parameters that the company uses, which is same temperature, same pressure, same flow rate, and in the same fluid that they're using. And we're going to tell them which inhibitor would work better for them. So this is simple applied research, but you could go beyond that research. You could actually see how this inhibitor interacts with the material, how it affects the corrosion mechanism. So you could go deeper, but you could start with a simple idea to do a service for a company, and you could take that service and build into it and enhance it to a deeper research and deeper knowledge. And that's where it becomes useful. We also look at the investigating material performance in the field. So you can do a lot of work in the field or in simulated field conditions. Other options are in material selection. So material selection is a big area to work on in Qatar. I always talk about how the international standards for material selection did not consider the Middle East standard. So it was mostly based on the Norsk standards from Norway on the North Sea. And as a result, lots of the conditions in Qatar, the high temperature that we talked about and humidity is not considered. So if somebody tells you in a plant, I've seen lots of failures, and they say, no, we use the stainless steel at 40 degrees, and stainless steel 316L, can survive up to 60 degrees. It's not true. Your operating temperature is not 40 or 60. Your operating temperature is 83 degrees in the summer. And so that's something that the operators are not aware of. And this is where the research community can come in and show the evidence that some alloys cannot be used unless you cool them, for example. Not all the corrosion-resistant alloys that we think of resist the environmental conditions in Qatar. I've seen duplex stainless steel failing in Qatar. I've seen nickel alloys failing in Qatar. So not everything works. And unfortunately is that a lot of expensive alloys are used in Qatar to prevent corrosion. A lot of overprotection is going on. There are some alloys that are not expensive and they perform well, but there are not many evidence. And that's where the researchers can come in and do the testing and do the research and show clear evidence. GREs have been started to be used around 10 years ago in Qatar, but people are not comfortable with them and they are not still used much. Their use is very limited, and that's an area that can be explored. So what are the challenges that we face? There are a lot of topics that we can work on, but we still have very limited industry-oriented research. Why we're having that? It's interesting, what you look at. If you look at my first point here, is that Qatar has the highest GDP in the world. So this should be good news for us. It's unfortunately, some are misusing this. So I worked in plants in Qatar. So if something fails, what they say, okay, it failed, let's replace it. We got the money. That's the attitude. They don't look at, oh, it fails. We have to go check and do a proper investigation and simulate the conditions in the lab, look at everything and find out what caused this failure and what should we do to prevent it using same material, using, maybe something even the same price. And so that's the problem, that people just get used to just replace things. RDI is still considered a new concept in Qatar. People don't understand what it is. The other problem we have is that professional development and training opportunities in Qatar are very limited to non-nationals. So you get people who work in the plants for 35, 40 years, and they maybe got training once. And then you come in with a new concept. You want to use new models, you want to apply new software, you want to put sensors to measure, to detect leaks. They don't understand this because their knowledge is 40 years old and they consider you a threat. So they don't support it. And these are the ones that usually block any research activities because it's not recognized. And that's the big, hard, wall that we need to break. The other problem we have is the access to the sites. It's very, very limited. It became very difficult recently to conduct field study because of getting access to the sites. The gate passes are very difficult. In 2019, we have samples in one of the sites, and we had to do 3 trips to the same site. Each trip takes over an hour. So we had for 3 days, we have to go back and forth because every time they ask for a new document so that we can get access to the site. This is knowing that we are getting a lot of support and forms stamped and signed by, one of the managers in one of the department in that company. Still, it's difficult to get access to the site. So that's also makes it challenging for us. And then the need for publications. Most of the researchers, unfortunately, like in many research institutions and academic institutions, your KPI is measured by the number of publications you make. And so you want to work with the industry doesn't like to publish. because they don't want to publish their problems or their process data. So this is the big hurdle. So you want to do a work, but at the same time you have to publish. So that's also a challenge. And then the lack of trust. The industry still doesn't trust researchers, doesn't trust academia. What could we do to overcome these challenges? So these are just some of the tips that I've done. I've been working with the industry for many years in Qatar, like over 12 years now. And what I looked at to build this relationship is that we have to work in enhancing this relationship. So number one, I think for us that we have a good card we have is the students. Students are ambassadors. So when you teach a student and when you put the research culture in the students' mind, so that's what I like. For example, QNRF is doing a lot of opportunities to make students, undergraduate students, like research and introduce them to research. When you get that, your students will go work in the plant, they will be your ambassador. In 3 or 4 years, they'll move in position and they will be the ones who would support research activities. So that's something that we need to invest in as much as we can. The other thing is that we need to do is to establish effective industry, research, academia work groups. We have the example of the Forum for Corrosion and Materials Engineering in Qatar. So when I created this forum, what I did, I looked at the industry need and I sat with them and I said, how about if we create this forum? And they said, oh, we don't want academia, we don't want research, it's going to turn to be research. I said, fine. Okay, can we have at least one member from each institution? They said, okay, one is enough. Okay. We went with this, we're going slowly working on them. But what we do also, we allow them to present. So it's most of the presentation in this forum are made by the industry, not by us. So that gives us an idea to hear about their problems, know what they need, and then we can come to them and say, we can solve this problem for you. And another thing we need to do is that the service to the industry is a good way to connect with them, but we have to have certified labs that can provide useful and reliable service. So you need to calibrate before you do your testing, because if you make one mistake, they're not going to come back to you. And you have to deliver things on time and on budget. So we need the industry to talk to us. So there are lots of conferences and workshops that I attended. And what I find is that it's mostly academia or research community talking and presenting, and the industry sitting. We don't want them to listen to us. We want to give them a chance to talk to us and tell us what they need. We need to speak their language. And lots of people ask me, when I say I speak the industry language, they say, oh, you speak Arabic. It's not the Arabic language. You need to know the industry language, what they actually look for. And it's usually financial impact. How much money they're gonna save if they follow this method that you're doing, if they do this research. You need to do that. You need to consider it. And what can you do with this? Please don't promise what you cannot do. So if they ask you to do something and you know you cannot do it, say, sorry, I don't know. It's not my area of interest. I can go read, I can look for somebody else to help me, but don't say that you can do everything. And if you don't understand what they say, ask for explanation. They talk about process, tell them to explain to you how it works. If you're meeting with them about a specific topic, prepare yourself, read, and be prepared for the discussion. Collaborate with others. Don't keep the work to yourself and say, oh, I can do everything. Today in the morning, I had a meeting where we have 3 people from 3 different institutions working in one project for the industry. The project came to us, but we go to them and ask them to help us because there is area we cannot cover. And that's how you can cover everything and you show a good example. Always think outside of the box. You have an equipment and you want to do a test and you want to simulate parameters, you can enhance it, you can change the design, you can do additions, you can build your own equipment. So always think about solutions. Very, very important for you to meet the deadlines and the budget. Industry deadlines and budget are firm. I would stay up all night to meet a deadline for the industry so that I know they'll come back to me next month with another work or another request. So that's very important. You have to gain their trust by doing your work, and never call your work research. Always call it R&D because they use R&D a lot, or call it technical service, but don't say research. And even though R&D is research in it, but they don't even look at what it means. We have a big hope in the RDI Council. We think that it may change the perspective of RDI in Qatar. Thank you very much for listening. I hope I didn't take long time. And if you have any questions, I'm ready to answer.
Thank you so much, Dr. Hanan. I think there's some echo. Okay. Thank you so much. And it was very useful, and it gives a very good insight to the mind of how the industry thinks and how our academic researchers can interact with the industry. I would encourage the attendees to ask questions. Type in your question in the chat window. You can type in during the presentation itself, or you can type in right now. I will start off with some couple of questions of my own to get the process going on. Dr. Hanan, in your opinion, what should be the balance between basic research and high TRL, applied research kind of projects when it comes to addressing materials challenges in Qatar, given your background in industry and how most of our applications we wanted to be commercialized and adopted in the industry. And also you need a good balance between basic and high TRL research. Can you please talk about it?
Yeah, they're both interconnected. And so if you start like with the applied, let's say you got a problem and you want to work with the industry in applied research, most of the local companies in Qatar, they are not interested in basic research. They're interested in problem solving. They're interested in applied research to solve one problem. But often when you work on that problem, you need to go back to the basic research to solve it. And so both of them work together, and you can start working in one aspect even to the application of product, but you need to get the basic going at the same time. So they work in parallel. I don't see us killing completely the basic research because we still need it. But what I see is that when you package it to the industry, never talk about the basic research, never go that deep. Just talk about the problem they have, how you want to solve it. And then while you're working on it, you can just go back and do a lot of great work on basic research. And I've often seen in so many research projects that I worked on is that we're working with applied research and we open the channels to 3 or 4 basic research that has been lasting years after that. And so I don't see it, as what I said, I don't see it dying. I see them working in parallel. You can't you can't reach a product without a basic research. It's still needed, but don't limit yourself to only basic, because you're killing yourself by doing that. You're not going to get any work.
Good. Thank you. You mentioned about students being good ambassadors for a link between academia and industry. Do you have a success story in that regard, or someone that you worked as with a student who later turned out to be a good connection? Can you please throw some light on that?
Yes, I've had several stories actually, and I worked at CNAQ where they have students, and even though my time what I taught at CNAQ was limited to 2 terms only, so I didn't teach much. I was working mostly in the industry-based research, but what I had is that some of the students that I taught and some of the students that I met or I gave, like for example, Dr. Bilal Mansour, I was a guest speaker in one of his lectures, and I gave a talk to some of his students, and eventually these students, they work in the industry, and then they have a problem, they come trying to solve it, so they'll come to you because they know the places where you work and they ask for solution, and then when you start working on it, they feel more comfortable with you because they know what you are doing and they trust what you are doing. And so, for example, in the case of Dr. Bilal's student, she came to us for a problem, but she came based on that lecture that I gave. She felt confident that I can do it, the same as the students at CNAQ. So what I'm saying is that if you invest well in students, and if you show them that they can trust your work, And sometimes people, when they teach lectures, they just go quickly with their lectures and they don't want to spend time talking about what they do in their research, especially for undergraduate study. They don't think the importance. The students don't know what you're doing unless you tell them what you're doing and you show them, you take them to the lab and you show them examples. These students, I have some students that reach management positions and they became decision makers. And they were my angels. You know, I wouldn't even go look for work with these companies. They will be the ones who come to me and say, oh, there is this work, you know, can you do it? So that's what I encourage everyone who has access to student to invest in.
Thank you so much. Thank you. I don't have questions, but I have people appreciating the presentation. I published the same. Probably they are still, the people are not sure how to ask a question in the chat window or something. But in case there are any questions, we will come back to it later also, and then we can take it from there also. Thank you so much, Dr. Hanan. That was very informative. And now I'll go to our next speaker. Thank you.
It's a pleasure.
Let me introduce our next speaker. The project title is Development of High Performance Metastable Aluminum Composites Using Microwave Sintering Approach, which is Dr. Abdul Shakur, Assistant Professor from Qatar University. Dr. Shakur is currently working as a research fellow in CAM, Qatar University. He holds a PhD degree in materials engineering. His area of research is synthesis and characterization of advanced materials for diversified applications. He's currently conducting research in novel cathode materials for sodium lithium rechargeable batteries, nanocomposite coatings for corrosion protection, aluminum metal matrix nanocomposites for automobile and aerospace applications. This particular project is related to the aluminum composites. He has published 116 indexed journal articles, 76 presentations in local and international conferences, 2 patents, 5 book chapters. He's currently supervising 23 international/national research funding grants, and he's a very active collaborator with local industries such as Qatar Steel and Qatar Shell. So please let me welcome Dr. Abdul Shakur with his presentation. Dr. Shakur, can you share your presentation, please?
Yeah, I'm trying to. Can you see my page or not?
We can see your video, but not the presentation yet.
I have shared the desktop. Now, can you see my screen?
Yes.
Thank you very much, Dr. Parkalan, for the nice introduction. Today's project is basically focused on the synthesis and unique characterization of aluminum metal matrix nanocomposites. In this project, we have developed some novel composition of aluminum metal composites using a microwave sintering approach. The novelty of this project was the novel composition that has been synthesized through a new concept, that is microwave sintering approach. because most of the aluminum metal composites, they are being produced through conventional sintering approach that carries many disadvantages as well. So in this project we have introduced a new concept of microwave sintering approach, which carries significant advantages over the conventional sintering approach. After the synthesis of different aluminum metal composites, their structural, mechanical and thermal properties were investigated, and we have got significant improvement in the properties as compared to the conventional sintering process. Before going into the detail of the technical discussion of the project, let me introduce my teams and collaborator. This project was jointly carried out between three institutions: Qatar University, Suez University for Egypt, and National University of Singapore. So from Qatar University, I was the lead PI, and Dr. Adil Muhammad, he was a PI, and Professor Manoj Gupta from the National University of Singapore, he was an active collaborator. Most of the work was done here in Qatar University through the postdoc, Dr. Panchal Reddy, who did a significant contribution to this project. And the second main contributor is Ms. Faria Ubaid. She did a lot of work for the development of new formulations for aluminum metal composites. Just why the composite materials are important and why they are being studied, that gives some motivation, because composite material is a good candidate for engineering application because of their wide applications in various sectors. Like in construction industries, they are being 34%, wind energy 8%, consumer 16%, industrial application 50%, especially in transportation, they are being used about 27%. So these are some areas which are being focused, and they are being utilizing the composite materials. Especially the today's your talk is focused on the aluminum metal composites, and they are finding extensive use in the transportation or automobile industry, mainly focusing on the car, buses, trucks and marine applications. The motivation behind the development of aluminum metal composites is because of the low density of aluminum, because aluminum is lightweight material, but it carries certain disadvantages because of its, although it is a lightweight material, but it has very poor strength. That is why, in order to improve the limitations and to extend the application of aluminum metals, so people are trying to combine it with different nano materials reinforcement to develop different kind of aluminum metal based nano composites. And that is why in addition to the aluminum metal composites, there are other various types of composite. They are being used in various sectors. So composite materials are very important materials, and which have found numerous application in various sectors. Beside these, composite materials, they are also finding their applications in, as I said earlier, in automobile industries, sports, and aircraft industries, defense and engineering applications, in aerospace industry, even in biomedical applications and in storage applications. So these are some encouraging fields in which the composite materials, they are being used. So to sum up, we can say that composite material is an important class of engineering materials which have numerous application in the field. Before going into the detail of the project, let me introduce the concept of composite material for the people who are not directly associated with this field. Basically, composite material is composed of a matrix material and the reinforcement. The beauty of the composite material is that when these two materials, they are mixed together, which are physically different and chemically different, the parent phases, when they are mixed together, the product phase, which is a composite material, that carries much superior properties as compared to the parent phases. So the outstanding advantage of composite material is that when the two different materials, they are combined together, they give a product phase that has much superior properties as compared to the parent phases. So there are there are different forms of the composite materials. I will show you in the next slide. Composite materials, they can be classified, on the basis of matrix materials and on the basis of reinforcement. For example, we can, in the matrix, we have metal, we can have a polymer, we have a ceramic, and there is people have also categorized carbon as a matrix material. So based upon these matrices, we can have metal composites, polymeric composites and ceramic composites. And based upon the reinforcement which are being used, we can also classify the composite materials into fiber reinforced composites, viscous reinforced composite, and particle reinforced composites. So these are the general classification of the engineering composites based on the matrix and the reinforcement. Let's talk about the aluminum metal matrix composites, because they have finding their numerous application in automobile industry. As I have introduced earlier, that because aluminum is a lightweight metal, and that is why it carries significant advantages. And the development of aluminum metal composites, they have important use in the transportation industry, or we can say in the automobile industry. For example, the drums, the rotor drums, they are being previously produced through cast iron, which almost weighs 71 pounds. However, when these are being replaced with the aluminum metal composites, we can see almost the weight is reduced to 38.5 pounds. Almost half of the weight is reduced, and we can see that once the weight is reduced, a lot of fuel consumption has been reduced. It is not only the economy that is related to the fuel consumption. However, it also contributes indirectly to control the environment pollution as well, because we are using less fuel, and that will less pollute the environment. So that is why the aluminum metal composites, they are finding extensive application in many automobile industries. As far as our research methodology is concerned, we use powder metallurgy route to develop various formulations of the aluminum metal composites. We started with the aluminum powder that has been mixed with various reinforcements like titanium carbide, boron carbide, silicon carbide. All the reinforcements which we used was in the form of nanoparticles. Then we have ball milling. Usually the process of mixing was carried out at 200 RPM for 2 hours, followed by the pelletizing and compaction to obtain green pellets. Then after the obtaining the green pellets, the green pellets were sintered through microwave sintering approach. For a direct comparison, we also sintered through conventional sintering approach as well. Then after the synthesis of the microwave, the sintered or the direct conventional composites, their characterization was carried out, physical characterization that carries density measurement, porosity measurement, and during structural analysis, the XRD and SEM images were taken. And then we have mechanical characterization that like hardness, strength, and then followed by the thermal characterization. And usually during thermal characterization, coefficient of thermal expansion was calculated and compared with the other materials. So this is the outline of the our methodology that was used in the synthesis of various kind of aluminum metal composites. So this is a schematic diagram showing the actual process, how it was conducted. We started with the aluminum powder and the reinforcement, then through ball milling, then compaction through hydraulic press, then the microwave sintering as done to induce the desired set of properties into the developed aluminum metal matrix nano composites. So just let me share the important features of the microwave sintering approach. Every people, they have microwave in their kitchen, and they are being used to heat the different food ingredients in that microwave. So basically microwave sintering approach has a different salient characteristics as compared to the conventional sintering approach. During a conventional sintering approach, the pellets are the green pellets, they are placed into the furnace, and the whole inner body of the furnaces get heated up, and the heat is traveled from outer side of the component to the inner side of the component, So whereas in case of microwave sintering, it's an internal heating process through the, presence of dipole into the material and the alignment of dipoles, internal heating started. And so it means that microwave sintering heating is an internal process, whereas the conventional sintering is a outer heating process. And if we compare the features of microwave sintering, we can say it is an internal heating process. It is much rapid process as compared to the conventional heating process, and we can a selected portion of the component that can be heated up, and it has high heating efficiency, rapid heating response, and we have a very good control over the temperature, and we can have uniform temperature throughout the component. At the last, it is a cleaner source, because many the direct sintering furnaces, they are using natural gas or oil, which carries the pollution to the environment. So to compare the microwave sintering technology with the conventional sintering technology, we can say that microwave sintering technology carries much advantages over the conventional sintering approach. The outstanding feature of microwave sintering approach is that the sintering time is much less as compared to the conventional sintering process. For example, in case of the conventional sintering process, the sintering time is usually in hours, 3 hours, 4 hours. But in case of microwave sintering, the time is only 20 minutes, 30 minutes. In our case, sintering time of 30 minutes was employed. That save a lot of energy and a lot of capital for the development of material, which is an important aspect for the development of any advanced materials. So we have developed many compositions for aluminum metal composites, but because of the time limitations, we will be briefly focusing on 4 compositions. That is aluminum silicon carbide nanocomposites, aluminum oxide nanocomposites, and aluminum boron, and aluminum titanium carbide nanocomposites. These are the 4 compositions which will be briefly talked about in today's talk. Let me start with the aluminum silicon and nano composites. As I have said, we started with the aluminum powder and silicon carbide powder. They were mixed together and they were sintered. And this is the XRD spectra of the various compositions that were produced. This is the pure aluminum, and then 0.3% silicon carbide, 0.5%. 1% and 1.5% silicon carbide. We can see this XRD spectra are very crystalline because of the crystalline nature of the aluminum matrix, and we can see that with increasing amount of silicon carbide, the reinforcement peaks are also introduced into the structure. It means that the silicon carbide as a reinforcement has been introduced into the matrix. And these are the SEM images of the developed nano composites. We can see that the silicon carbides, they are incorporated into the aluminum matrix, and this is the EDX analysis showing the distribution of silicon carbide into the aluminum matrix. So this is the the hardness versus silicon content graph. We can see that the hardness of the aluminum matrix is going to increase with the increasing amount of the silicon carbide, which is as a reinforcement. I will explain why it is going to increase with increasing amount of silicon carbide. So here is the compression testing results of the developed the nano composites. We can see that yield strength and ultimate compressive strength, they are going to increase with the increasing amount of silicon carbide contents in the aluminum matrix. And this is the tensile testing of the developed aluminum silicon carbide nano composites. We can see that the strength aluminum is the increasing, whereas the elongation is going to be reduced because we are adding a brittle phase. Silicon carbide is a brittle phase into the ductile matrix, which is aluminium. We can see, and we have summarized calculated values of yield strength, ultimate tensile strength, and elongation. We can see that the yield strength and the ultimate tensile strength, they are going to be increased, whereas the elongation is going to be decreased. Similar behavior is we found that during nano indentation, we have all the developed nano composites were tested under a constant load, about 100 millinewton, and and we studied the depth of penetration. We can see that the depth of penetration is going to be decreased with the increasing amount of the silicon carbide contents in the matrix. And here is, you can see that, the hardness and the Young's modulus, they are going to increase with the increase in silicon carbide nano contents. Why? There is an improvement in mechanical properties like hardness, strength, and the yield strength with the increasing amount of, silicon carbide contents in the matrix. The reason is because there are many factors that contribute. The main reason is through the dispersion hardening phenomena, because the presence of hard particles into the matrix, they impede the movement of dislocations. That is why the strength is improved. Secondly, because through the rule of mixtures, we are adding a hard particles into the soft matrix, and with the increasing amount of the hard particles, the strength will naturally improve. Also, beside these two factors, the presence of the ceramic particles also increase the load bearing capacity of the aluminum matrix. That is why we have seen that there is increase in mechanical properties with increasing amount of the silicon carbide nanoparticles into the matrix. So these are the fracture morphology of the developed materials. Aluminum, the pure matrix is to have a shear mechanism, shear bands, whereas in case of our developed composites, we have very clear dimples into the structure. We also studied the coefficient of thermal expansion of all the developed composition. We can see that the coefficient of thermal expansion going to decrease with increasing amount of silicon carbide nanoparticles into the matrix. It means that this is very important criteria, because in automobile especially in the moving parts, the coefficient of thermal expansion is very important, because the two moving parts which are moving relevant to each other because of their movement and the presence of temperature, if there is a high thermal expansion, they may choke together. That will hinder the performance of any vehicle. That is why the decrease in thermal coefficient has some useful impact on the performance of the moving parts into the automobile. The second composition I would like to share is the aluminum oxide nano composites. So we have.
Sorry to interrupt. You have a couple of minutes to.
Okay. Let me quickly, So these are the XRD spectra of various composition, and these are the SEM images which shows the distribution of aluminum oxide particles into the matrix, and we can see the density and porosity increases with the increasing of the contents. Similarly, these are the mechanical properties. We can see that the strength and the yield strength increases with increase in the alumina particles into the matrix, and these are the nano indentation behavior. Similarly, we can see that the micro hardness also increases. The reason is same, which I have already discussed, because of the dispersion hardening effect and the load bearing capability of the synthesized aluminum metal composites. The third composition we have developed is aluminum boron nano composites, and various the composition were developed, and we can also see that the strength and the hardness, they are being increased with the increasing content of the boron nitride, and the thermal coefficient is also going to decrease with the increasing boron nitride contents into the composite. And these are the some mechanical properties as I have discussed earlier. With the increasing amount of boron nitride into the aluminum matrix, we have seen improvement in the tensile strength, in compressive strength, and we have observed a reduction in the elongation. So this is also similar results as I have explained earlier. So the final composition is aluminum titanium carbide nanocomposites, and the similar trend were observed. Let me explain the AFM results. The surface hardness increases with increase in TIC nanocarbide contents into this matrix because of the increase because of the presence of TIC particles into the matrix. The hardness increases with increase in TIC composition into the aluminum matrix. So let's come to the output and the impact. During this project, we have published 13 SAE index journal articles, 1 book chapters. We have made 12 presentations and 2 conference proceedings. As far as the impact is concerned, the development of a novel formulation with promising mechanical, structural and thermal properties, it is anticipated that they have good applications in automobile industry, and the lot of fuel consumption is reduced, and because of the utilization of less fuel to drive the vehicles, we think that it has an indirect impact on the our climate and the environment. There will be less pollution because of the use of less fuel into the being injected into the automobiles. So just as a final slide, let me acknowledge the Qatar National Research Fund and PRP7. The project was funded through this research grant. We also acknowledge, the Qatar University Center for Advanced Materials, in which the actual research was carried out. I would like especially to thank Professor Gupta from the University of Singapore, who collaborated very actively in this project. Thank you very much, and I am ready to answer if you have any questions.
Thank you so much, Dr. Abdul Shakur. It was a very nice presentation, and you have a lot of impact through journal papers and conferences. So congratulations. There is one question here, I think, which is for you. Someone wants to know, what is the speaker specialization? Is this available in Qatar University? What is the name of the major? And I'm thinking to enroll my son in the same field, and it looks very interesting.
So actually in Qatar University, we have students from mechanical engineering, chemical engineering, and even some students from College of Arts and Science. They are being collaborating with us, and we have given in the past some assignments. So from any majors, usually from mechanical engineering, chemical engineering, and even the students with chemistry backgrounds, they are usually joining this research work. It's a nice opportunity because nowadays it is a interdisciplinary research. It is not only the one kind of research. Many disciplines, they get together to find some new materials for various applications. So as I have said, mechanical engineering, chemical engineering, and students from chemistry background, they are being introduced into this research work.
Thank you. There is another technical question. How do you investigate the hardening mechanism with respect to reinforcement materials?
Yeah, basically, in the literature, it is well reported, the dispersion hardening mechanism, because, once the soft matrix is reinforced with the hard particles, that basically block the movement of the dislocation. Basically, plastic deformation is because of the movement of dislocations. So once there is a hard particles or barrier to the way of the dislocation that don't allow the dislocations to move further, and the dislocations, they are being blocked over there. So that is why we can see that with the increasing concentration of reinforcement into the aluminum matrix, the hardness, tensile strength, and the yield strength, they are going to be increased. So this is the indirect measurement of the the hardening or strengthening mechanism.
Okay. A question from my side. How do you think this process will perform the microwave sintering if you upscale it to the industrial scale level? Do you see any challenges if you upscale it?
Actually, now we are trying with the help of Professor Gupta. So we are doing it on a bigger scale. We have combined this research with the extrusion process as well. To produce actual components, because once you have a extrusion process into the this materials, their properties are much improved, and I don't feel any major challenges if we can scale up this process, because we can have sintering technology that has been well adopted in the industry as well.
Thank you so much, Dr. Shakur. If there are other questions, we will come back at the end of the presentation.
Thank you. My pleasure. Thank you very much.
Dr. Hanan, are you still there? We have a few questions. Maybe they typed in late.
Yes, I am still there. Yes.
Okay, thank you. Let me read out the question to you. Someone wants to know if there is a problem to be solved, but they do not have a team and have not done research before. How do they start, and what is your advice?
I just read that question and I laughed, because this is how I started myself. Okay. So when I started doing this work, I was working in the industry in Qatar, and then I left the industry and I started working with CNAQ, mostly to work for QP through CNAQ, I guess. But I was doing my PhD during that time. And so I was working on my thesis, writing my thesis, and I started at CNAQ with pretty much no equipment and no research experience in Qatar, only industry experience. And what I did is that I used students. So students is a big asset. I hired through my work at CNAQ, I had 32 students working with me in total. And so what I did, when you have a PhD or when you had a master, you learned how to do research. So it's not new to you. And so the idea of working on research is not difficult. The big challenges is equipment and people who help you, especially if you have a full-time job doing something else. And so what I did is that, number one, I was using others' equipment. So thank you to University College of London. They were very supportive to research. They allowed us access to their equipment. They trained us how to use their SCM. And so we had access, full access to the SCM. We just book it. We used their optical microscope, because at the time our microscopes were old. And then eventually we bought our microscope, we bought our SCM, we bought our potentiostat. So we started from nothing, no equipment and no people. And students are usually hiring students, undergraduate students, is not expensive. So student, when they want to learn something, so it's a practical experience for them, and the cost is not high. So the start was simple. And then eventually I got my funds and I was able to cover their costs and go beyond that to hire even a PhD person to work with me. So you can start, but you need to find a way. And to answer this question, really, I want to emphasize one thing. We in institutions, either research or academic institutions, should have our doors open to work together. We should help each other. We don't need to have so many equipment repeated in all the institutes. We should be, all of us, having access to, not open access, but enable us, each other, to use each other's equipment under supervision. But we don't need to buy the same equipment that others have, because that's just waste of cost and efforts.
Okay, thank you. I have one more question for you. Professor Faris, please hold on. I know you are next in line. I wanted to finish the questions, otherwise it will be confusing later. So there is a question to Dr. Hanan. Could you please elaborate more on the Qatari industrial needs for materials working at high temperature and extreme conditions, especially polymers?
Okay, so Qatar needs a lot of, the industry, the process, they work with high temperature and high pressure. So they need material that survive these conditions. To my knowledge, there is very limited. At least I'll talk about the national companies. You know, I cannot talk about Shell's process or Total, but as far as I know, with the national companies, the use of polymers in high temperature is not really being used much. I didn't recall seeing any case with polymer in high temperature, so it's not used much. With the pressure, I've seen it used with high pressure and very limited, and with care, like they're careful. They're not, they're very cautious because they are not aware of the properties of the polymers that can make it as a, you know, good option and cheap option. So that's what we would think the research community can contribute by showing examples that this would work for us. But we don't have any examples, at least in the national companies level, as far as I know, I would say.
Okay, thank you so much, Dr. Hanan. Now I'll introduce our next speaker. Thank you. We'll move on to our next speaker. The project title is Direct Metal Laser Sintering Technology for Manufacture of Fully Porous Functionally Graded Titanium Alloy Femoral Stems. This is going to be presented by Professor Faris, Qatar University, and he's also Director, Qatar Transportation and Traffic Safety Center. Dr. Faris is currently a professor in the Department of Mechanical and Industrial Engineering at Qatar University. He joined QU in 2013. Prior to Qatar, he has spent 12 years in the field of academics in Malaysia. He has obtained his degree from Purdue University and University Putra, Malaysia. His research and teaching are in the field of design, additive manufacturing, applied mechanics, road safety and engineering. He has been a LPI successfully for over 10 national research grants. He has supervised over 200 undergraduate senior projects, 5 PhDs and 21 master students. Is published in over 100 papers. He has also held several administrative duties. Currently, he is the director for Qatar Transportation and Traffic Safety Center at QU. Dr. Faris is a chartered engineering with Engineering Council of UK. He is also a fellow to Institution of Mechanical Engineers UK, and he sits as an editor for a few peer-reviewed journals. So please, Dr. Faris, you can start your presentation now.
Good morning. Thank you, Dr. Para. Can you see my slides?
Yes.
Okay, great. So today's talk is, the title is quite a lengthful title. Basically is, I'm not creating a new material, but rather I'm using titanium metal powders with 3D printing to design and develop new hip implants. So the benefits of 3D printing is that it's capable of fabricating complex structures, and we want to see if we can use this ability to create complex structures that can give a better performance for the hip implants. So in general, this is the focus of the paper, and the main approach adopted mainly is design and computational approach. So I'm Faris from Qatar University, and allow me to introduce my team members. In general, this project was handled by 3 universities, by Qatar University, University Malaysia Pahang, and University Malaya. The team from University Malaysia Pahang assisted in the 3D printing part, and the biomedical aspect came from the University of Malaya, and together we worked on this project. So as you all know, I mean, the femur bone, all right, plays a vital role in supporting our structure through the hip joint, and sad to say, people with osteoporosis and other bone diseases are very prone to hip or femur bone fracture. This is not uncommon. This is a very common phenomena globally, and there are many reasons that lead towards the femur fracturing or the failure of the hip joint. Mainly is due to the bone strength, and within the bone strength, there's a lot of other factors that contribute to the bone strength, and also due to impact. Usually is when either you have a fall. This is very common in elderly people, especially females who have osteoporosis, and when they have a fall, it will lead towards a high impact on your bone and cause fracture. And also during trauma, for example, an accident can happen to young adults. The accident can be through automotive or through sports where there's a high impact on the bone and the femur bone fractures. All these conditions requires for hip replacement. And the hip fracture is not something that you want to face. It will cause a lot of discomfort and will affect the quality of life. As you can know, the femur or the hip bone is actually carrying the weight of the body. So this joint is very crucial to have a good quality of life. Now, this is a burden? Yes, this is a burden, and every year the number of fractures are increasing, and mainly due to the lifestyle that we have today, where obesity is in a rise, and obesity also leads towards poor bone quality and extra weight on the bone, and this causes increase the factor for bone fracture. So femur bone fracturing leading to hip failure is not uncommon, as I said earlier, and this is an issue globally. Right, if you allow me, just to give you the market of just the hip replacement itself, the whole process, the market currently is around 7.13 billion, and by 2026 it's expected to reach around 10 billion. This is the market size just for hip replacement, not looking at other joints in the body. So as you can see, it's a very big market, and this is something that is happening very frequently. So the hip fracture, as I mentioned, is unavoidable and it's a billion-dollar industry. But what is important within this hip replacement is that between 5 to 15% of the patients who have received this knee replacement are required to undergo a revision surgery. That means second surgery. Why? Because the hip implant failed after a couple of years in the patient. So this hip revision is a very costly process. It's very complicated. It takes more time, and it's something that we want to avoid, if possible, for patients who are receiving the hip implants. So the focus of this study that we have today is how can we look into new designs of implants to improve the performance of the hip implant and to reduce the need for revision surgeries among the recipients. Right. There are many reasons why patients or the recipients of the hip implants undergo a revision surgery, as shown in this diagram here. One of the main reasons is what we call aseptic loosening. This has been reported as one of the main reasons patients undergo a revision surgery. And within aseptic loosening, we can characterize it into three major factors. One is the patient factor, one is the surgical factor, and one is the prosthesis factor. And as you can see, there are a lot of factors that contribute towards this type of failure. So the focus of this study is looking more into the prosthesis design. How can we improve the design? So we are handling more on the design factor aspect of the implant. Now, the main reason that within this design aspect is the why the implants fail is there is a mismatch between the stiffness of the implant and the femur bone. So usually the traditional implants that are out there, either from cobalt chromium or from titanium, they are much stiffer than the bone stiffness. So what happens is the implants tend to take the weight or the load of the body, and the femur bone is not stressed. So because of this, the femur bone undergoes stress shielding, and because it undergoes stress shielding, it loses density. So once the femur bone loses density, the surrounding quality of the bone with the stem decreases, and this will affect the stability of the implant in the femur bone. resulting in the failure of the implant and the requirement of a revised surgery for the implant. So the research question that we had in mind is, can we reduce the stiffness of titanium, bulk titanium, by introducing cellulose structured femoral stem? That means instead of using a dense bulk titanium, can we design a complex structure within the titanium, whereby we are still using titanium, but due to the cellulose structure by nature, we bring down the stiffness as close as possible to the femur bone, such that we can reduce the stress shielding and therefore improve the stability between the stem and the bone. So that is the research question that we had in mind. Now, the main objective for this study is that we were looking into developing a fatigue design space for seamless porous stems, where we hope to achieve the stiffness of the stems as close as possible to the femur bone. At the same time, we're trying to reduce the stress shielding, all right, and finally enhancing the stability by increasing the contact between the bone and the implant. And most of the work was done computationally, and we did 1 or 2 fatigue testing. So this is the limitation of the study. Allow me to share with you a flow chart. So basically, the whole project was a design-based through computational approach. We had 2 aspects. One is looking at the stress part, and one is looking on the stability, basically the bone growth around the stem. And from this, we came out with novel designs, porous structures, which achieved the objective of the study. And at this stage, we achieved a TRL of 2 of 3. Is this a proof of concept? Right, so let me give you an overview of how we proceeded with the study. So generally, we looked in general the microstructure part. How can we design a porous structure? And then we did some sensitive analysis to play around with the size of the unit cell of the porous structure to make sure that we achieve the effective properties close to that of the bone. And once we have designed the porous structure, we had this porous structure embedded into the stem, where the outer part is a dense shell and the inner part is the porous structure. So this whole combination gives us our femoral stem. So again, to repeat, the outer part is a dense shell within 0.5 to 2 millimeters. These are our design parameters. And inside of this dense shell is where we embed the porous structure made from titanium. So this whole volume here, all right, of this porous structure reduced the mass of the overall implant compared to the bulk titanium, and also managed to reduce the stiffness of the bulk titanium close to that to the bone. And then by using the ISO standard, we managed to conduct our studies again through the computational approach. All right, so the first step was we created few microstructure unit cells, all right, and then we look at which of these microstructure unit cells, all right, after going through all this process here, are giving us properties which are close to the femur bone. All right, so this is the roadmap that we took, and once we found the properties of the microstructure and the way to design the microstructure to achieve a ultimate stiffness close to the femur bone, that was our design. So then we used that to construct the full implant. So this explains the approach. So we basically played with different porosities of the microstructure. We had some compression tests to determine the elastic modulus and the yield strength, and then the best candidate gave us the full model of the stem. Once we achieved the full model of the stem, we proceeded in 2 aspects. It was reported in literature that cellular structures have a fatigue strength of about 0.3 of the yield strength. So taking into account this finding in the literature, looking into account the stiffness of the stems, trying to push it close towards the bone stiffness, and looking at the stresses in the dense section of the implants, we created a design space. This design space is basically where our design parameters will fulfill the requirement of the implant. And to strengthen this further, we went into actual fatigue analysis. We used the Soderbergh approach, and we created another design space from this approach, and then we combined both the design space in a more conservative manner to achieve the final design space, which we will share with you later. So again, this final design space allows designers to select the design variables to be customized for for different patients. So that's the idea of creating such a design space. All right, now in terms of the stability, the first part which I showed to you was for the stress part. In terms of stability, again, our focus was more towards cementless implants. So when you have an implant in the bone, you have your metal, this is your implant, you have your bone, and then you have the interaction. Traditionally, most of the implants, they use a coating, all right, onto the metal, and this coating is a spread coating, and it's very random. So we want to bring this one step forward, and we want to design the way we do the coating, and that is through introduction of beads, arrangements of pores or beads on the stem to improve the anchorage between the metal implant and the bone. So we played with various combinations on how we can arrange the pores or the beads on the outer surface of the implant and see which of these configurations allow better bone growth, which in return improves the stability. And we basically develop our own algorithm where these are the various options of can you hear me?
Yeah.
Yeah. These are the various options of designing the pores or the beads. And then we have the finite element model. And here, what we had is we have developed an algorithm that simulates the bone growth by looking at the strains on the tissue. So various micromotions lead to different strains, and these strains lead to different promotion of bone growth. So there was an algorithm developed, and we use this algorithm to study if a particular design of the pores or beads actually enhance tissue growth on the stem. This tissue growth is needed to enhance the stability between the implant and the bone. So in terms of results wise, this was the first design space we created. So we have many other sub design spaces that we use to construct. We have many design spaces that we use to construct this design space. So this allows us to look at the design parameters, and we know exactly in which space we are safe. So therefore, we can use the design parameters in that space to construct our final design for printing purpose. Okay. Right. All right. So let me just go back one slide. Sorry for that. Okay, so the second design space, that is the final design space. That's where we incorporated the design space on the left with the Soderbergh approach. So the gray area is the targeted area that we will use in selecting design parameters that we will later fabricate and test for our fatigue testing. In terms of stability, all right, based on the algorithm developed, you can see here the iterations here refer to time. This is a time-based iteration where it's all right, and these are something wrong with my laser. Okay, and the top part here, the 200 micrometer pores, 800 micrometer pores, the FG, these are the various design of the pores that we plan to put on the outer part of the stem. So as you can see here, as I mentioned earlier, the iterations are the time scale. So as time progresses, we can see that for some designs, there is little bone growth, but for some design, there are more bone growth. For example, for the FGPD pause, after 60 iterations or 60 time scale, we managed to achieve a mature bone, which is what we want to achieve. So these findings showed that the different pore designs actually affects the way you increase your stability. And this study shows that we can achieve a significant bone growth, at least through the computational approach. Once we have done the design space and we have got the pores designs as the coating.
Dr. Faris, you have a couple of minutes.
Sure. So the next step is we actually printed this in our lab. So this is our 3D printing machine in College of Engineering, Qatar University. This machine is capable of printing many metal materials from cobalt, chromium, titanium, stainless steel, Econel, and so forth. So finally, we managed to design. We have a final design here, and we managed to print the stems, and we tested the stems in fatigue, and they achieved beyond 5 million cycles, which is what we are looking for. But there's still room for improvement, but this is a good achievement for a concept stage. So all this was done here in Qatar. And the outputs is we managed to achieve a low porous stem of 20 gigapascal, quite close to the stiffness of the femur bone. And we managed to reduce the stress shielding by 30%. So most of our targets in the projects were achieved. And also with our new approach in the algorithm for stability, we have proven that we can enhance the bone growth along the stem by designing certain pores or bits on the outer part of the implant. Now, in terms of benefits, this study shows that we have capability of designing new implants which can be customized for patients. Currently, most implants are in the market are not customized. They are bulk design. So the surgeons during the surgery will adjust the fixtures in the stems to fit the patients. But with this now, we can have specific implants designed for patients based on their bone strength, based on their height, their weight, and so forth. So this is a concept that we just came from this study, and we are happy with the concept, and we hope to bring this forward. So we just completed stage 1, and there is still a long way to go before we can actually see this in the market. Stage 2 basically is we have to further enhance the experimental study in terms of more fatigue designs, more fatigue testing, and improving the design, and then followed by some cadaver testing, where we will put this implant in cadaver legs and use some hip simulator overseas to see the performance of the implants in the actual gait cycle. And once stages 2A, 2B are clear, then maybe perhaps in stage 3, we are looking for some clinical trials if that is possible. But the whole duration from 2 to 3 will take around 7 to 8 years before we can actually see a finalized concept to be commercialized. So the research work has given us 6 papers, which we are happy to publish with the team. And this final note, I'd like to thank QNRF for funding this wonderful project. Also to Qatar University, who have provided the facility and supports, and to all my team members who contributed to the success of this project with the publications. And with that, thank you, and I'm happy to answer any questions that the floor may have.
Thank you so much, Dr. Faris. There is a couple of questions. Before that, I will ask a question from my side. How does this research that you're doing compare with the state of the art in additive manufacturing applied to orthopedic implants?
Initially, the 3D printing in orthopedic implants were mainly focusing on dental implants. And lately, in the last, I would say maybe 6-7 years, there's interest into the hip implants because mainly confidence, because teeth implant is not that crucial compared to hip implants where it bears your body structure. So in the last 6-7 years, there was more confidence in metal manufacturing, and now lately I would say that this interest has grown, and many key players, many key industries at DPA and in Zimmer are looking into using 3D printing for implants in general.
Okay, I'm going to read out the question here. Someone wants to know, is this design going to be manufactured in Qatar, or has it been tried by a surgeon in HMC on their patients yet?
Yeah, as in my second slide, I mentioned that we are still in TRL 2 or 3. So it's still a proof of concept, and if we do get funding, which we hope to get some funding, we plan to improve the TRL by looking at lab scale, which is doing more fatigue testing, to do some cadaver testing to improve the design, and then only we may proceed with the clinical trials. The whole process will take easily another 6-7 years to 8 years. So to answer it short, it will not be in the market now. With sufficient funding and success in the coming years, if this is to be brought forward, we should see it maybe 9 or 10 years in the market. As you know, most implants worldwide will take years before they reach the market.
Okay, thank you. Another question is, how about the mobility of the implant after several years of usage?
As I said, many people who have these implants, all right, it differs from patient to patient. That's one. And from what's published out there from the surgeons, orthopedics, and from the medical side, typically 5 to 15% of the recipients of these implants will have to undergo a revision surgery within 5 to 10 years of receiving the first implant. So I would say the rest of them, they will have a good quality of life with the implants. And again, as I shared earlier, there are many factors that causes this failure. For some, it can be the implant design itself. For some, can be other factors, for example, the patient or the surgical factors.
Okay, thank you so much, Dr. Faris. I will move on to our next speaker now. Thank you once again.
Thank you.
Our next speaker is from Texas A&M University at Qatar, Dr. Mohammed Al-Hashimi, Research Associate Professor. His project title is Directed Self-Assembly and Alignment of Conjugated Polymers for High Performance Plastic Electronics. Dr. Al-Hashimi received his MSc Honours degree in pharmaceutical chemistry in 2003 and PhD in 2007 from Queen Mary University of London, UK. In 2012, he joined Qatar University as assistant professor, and in 2013, he joined Texas A&M at Qatar. He serves on the editorial boards of 2 journals, Organic Chemistry and Current Organocatalysis. A significant project management experience both in industrial and academic settings. He's published over 65 peer-reviewed papers and 4 patents with a H index of 25. He's a recipient of several awards from UK and Malaysia. Most recently, he's been awarded in the ARC 16 and TOMQ Faculty Research Excellence Award in 2020. He has extensive experience in organic polymers with focuses in design, synthesis of organic semiconductor materials for a range of optoelectronic applications. His other interest centers on development of novel polymeric materials and the synthesis of recoverable, reusable, homogeneous and heterogeneous catalysts. So please let me welcome Dr. Mohammed Al-Hashimi.
Thank you very much, Dr. Parkalan, for the kind introduction. And I would like to start off by thanking QNRF for the kind invitation to demonstrate the work that we've been doing for this sponsorship. So this project is basically in collaboration between Jingsu Kim from Michigan University and Lei Fang from Texas A&M at the State, and obviously myself from Texas A&M in Qatar. So I'll start off briefly by talking about a brief introduction about the current plastic electronics material and organic photovoltaics material that are used using these conjugated materials. We'll discuss some of the results that we have made, we publicly available for the research. And finally, I will conclude with some of the future outlooks. So my group basically looks into different areas. One of them is nature-inspired materials, and basically we look into these materials for plastic electronics. So the project is also with Leifang, which we also look into ladder-type materials to make these polymers even better. And also we look into 2D and 1D materials for conjugated polymers in terms of catalysis and other stuff is related. Aligned with these conjugated materials, we would like to make them directly aligned by fluorinates in different rings to give us a better effective ability for these materials. So it all starts off basically by when we're in school or younger, we are taught that plastics insulate and they do not conduct electricity. However, the Nobel Prize was awarded in 2000 to the three guys, Alan Higa, Mick Dimitri, and Shirakawa, by discovering a new class of material, polyacetylene. So this basically started the field of conductive polymers. And how basically it started off, if you look at these conductive materials for plastic electronics, they're involved in a huge array of materials, spanning from transistors to batteries to spintronics. Now you could even use it for lasers, solar cells, for photoacoustics, and even medical applications. The market for this is huge. As I said, basically due to the obviously COVID-19, things have shifted slightly, but the market is going to increase to about 6 billion in 2025 for these plastic electronics only. So the flexibility is enormous because you could use them for optical sensors, we could use them for health monitoring, which I'll speak later on about. We could even use it for prosthetics. And now the current field that's obviously is very important and is booming off is these self-healing materials for electronic skins. So having electronic skin is very, very important. And as you can see, I've demonstrated some of the figures where the CAGR will be increasing by up to 9.5% in some areas. Transistors are not new to the field. They've been around for a while now. Most of you can remember, obviously my generation, you can see the phones growing from having a huge, enormous phone all the way to this little slick, small smartphones for these iPhones that we have. At my age, I remember that I used to have the first phone that I had was a Nokia-based phone, which was like that. So if you have a Samsung phone, these are made out of plastic conjugated in terms of conjugated polymers that we'll be discussing hopefully today. Also, these materials have another important aspect to them, not only in plastic electronics, but in solar energy. So currently, if you look at Earth's inhabitants, energy that we utilize per year is about 400 exajoule. However, the sun produces more than 11,000 exajoule in one day. So we're only using a small fraction, the gray part over here, where all the yellow part is free and available for us to utilize. As we know, the Earth population is going to be growing from 6 billion to about 9.4 billion in 2050. So we have to reduce our per capita. So a huge amount, so obviously noticed about 7,500 to 15,000. So we need to find alternative energy source and other materials, advanced materials that don't consume that much energy. This slide over here from BP Solar have predicted that 10% of the world's energy is going to be utilized from OPV or PV materials in particular. We could reduce the carbon dioxide emission in a huge amount if we do use alternative materials. This is that was broadcasted or even published till 2040, and this is what they predicted. So we could reduce it from 7 G-tons of carbon dioxide, which was produced in 2000, if we utilize materials that are better than the current materials that we have. Lots of companies obviously involved in plastic electronics and solar energy, and some of them are shown here. Samsung, for example, as I mentioned, TVs, phones are involved in these plastic electronics. And to my surprise, obviously Shell, Japan, is involved heavily in material synthesis and plastic electronics, and currently, recently, Total as well. Other companies also, Germany has invested a lot, UK, US, Denmark, all these have been used, companies that are investing a lot in plastic electronics and solar energy. So what does my group look into, and why particularly organic materials? So organic materials are very important in the case they're low cost, and obviously cost is the biggest issue that we have. So they're low cost, we could cover a large area, and the most important thing is we could do roll-to-roll process. They give you the flexibility that other materials don't. And we could obviously change and modify these materials according to what we want and make them what we want. However, there are challenges associated with these materials. For example, their environmental instability, okay, and their lower performance. I've put lower performance in terms of that we've reached 15%, and yesterday or about 3 days ago, these materials have reached 18%. So it is increasing dramatically, as we say, since we've been back in the last 5 to 10 years. So if we want to visualize the future for 1 second, think of materials that could be low cost. We could reduce the carbon emission, carbon dioxide emission in particular. And imagine there are currently about 1.5 billion people out there without electricity. If we can make materials that are affordable and cheap, everyone in the world could have a better life. So visualizing the future for 1 second, if we could learn from the materials that we have from graphene, implement it into the plastic electronics or conjugated materials, we could derive new materials basically that are advanced and new energy source could be obtained. We don't have to rely on hydrocarbons from the petrochemical industry. We could leave the hydrocarbons for more essential stuff, for the pharmaceuticals, for advanced material processing. So that is basically the idea. I'll show you this part as well, where I've talked about organic. Organic is around here, about 17 to 18%. And you can see other materials have more other efficiencies, which are quite highly up. So what are these organic materials useful for? I'll show you some of these photos that were taken basically in South Africa, where they utilize these organic materials to demonstrate some of the applications of them. And you can see that these materials could basically utilized on buildings or even on stadiums. So for example, in Qatar, we have the World Cup coming around soon. Imagine we could have a stadium where during the day, all the sun basically is absorbed, and then you could turn on the stadium at night with these materials. If you've been to Singapore, for instance, there's a park in the middle. Imagine we could have these materials that are organic based, flexible, that absorb the light during the day, as I said, and it lights up the park during the night without using any electricity. Other aspects of these plastic electronics, I had a video, but I'm not going to play it in case it might not work. So these have huge amounts in medical applications, in gaming. Again, a lot of people like to read on the plane. All of us use iPads. Imagine you could download the material that you have on a small pen and then basically read it at your own convenience. Also, you see the iPads that people have. A lot of people are using iPads. It could save storage and space. Recently, the project allowed us to publish the nice high impact, one of the highest impact papers, I think, in research with 52, based on designing flexible and stretchable electronics. So if you're interested, please have a dig and read more about these flexible electronics that we have demonstrated. So what was the idea of the project? The idea of the project was, can we utilize sustainable materials, okay? Fabricate them without using any halogenated solvent or mild process conditions. Can we have an economic atom economy in terms of it's non-toxic? Can we make materials that are biosustainable and renewable? Unfortunately, most of the time, till now, even we need to utilize the petrochemical industry to make these materials. Can we avoid that? However, the truth is, we still need the petrochemical industry to derive our starting material. Can we use something alternative? Can we make it sustainable without using any fossil fuels? However, waste is another problem as well. So when you have conjugated materials or any materials, you're generating waste. Can we improve biocompatibility, which would lead to better bioelectronics? Fortunately, it's predicted that in 2050, there's going to be more plastic in the sea than fish. So obviously, fish lovers are going to suffer. And plastics are known to be notorious for obviously getting disposed of. But that's a problem. So where was our starting point? Can we avoid using fossil fuels, as I said, and use a nature-derived material to obtain a conjugated material that we want? Can we make it sustainable? Can we make the entire material sustainable, derived from nature? Having a material with a furane that could be obtained from corn, having side chains that could be obtained from coconuts, and obviously nitrogen and all other sources can be available. Can we do something interesting? So my group looks into thiazole materials. The medics or the people that work in the medical field know these thiazole materials are very useful. They're building blocks, okay, for anti-cancer and antimicrobial behavior. They're available in many varieties of foods that we eat and everything. It's based on a 5-membered nitrogen and a sulfurane. So can we make materials based on this thiazole or you could call it pyrrole system that could obtain efficiencies or mobilities for plastic electronics. So the idea basically, as I said, we need to learn from graphene, and can we make ladder type materials that could be also thermochromic? So for example, at night or even during the day when it's hot, the material lets light in, but it stops any of the heat coming through by changing color. Can we do all that and have the material to be intact? So as I said, graphene is very good for that. However, the problem with graphene is its flexibility. With these conjugated materials, we have the problem of torsional defects. So basically they rotate and they cause problems. However, graphene doesn't have that. We would like to make a material, or we aim to make a material in between these two that eliminates these torsional defects, that is similar to graphene, but can give you solubility. So the work was perceived really well by the research community, and they liked our work that they put this on their front cover in Chemical Science on 2 different occasions, in 2016 and 2017, where we demonstrated that we can make materials that are that. I will speak to you a bit more about them. Also recently, Chemistry of Materials highlighted the work on their front page, where we use these for plastic electronics, as I said, and we made some nice materials. So the postdoc that was working on the group, Maciej Barlog, the idea was to implement and put these thiozols, as I said, the nature-derived or thiazole-based electron-deficient system on these ladder-type system. I'm not going to talk about the synthesis, I'm going to keep it basic, but we managed to make some different materials having different alkyl chain to give us the solubility for these materials. We made some polymers, and as you can see from the table over here, the highest mobility we obtained was 0.87. I should just highlight this. This is probably one of the highest mobilities reported to date with these type of thiazole materials. Usually the values go between 0.2 to 0.5, but 0.87 is one of the highest reported to date. We were also interested not only to see if thiazole had an effect, but can we change a heteroatom? For example, as we know, sulfur is naturally also available. Garlic contains a lot of sulfur. Can we change sulfur? Can we change the carbon or nitrogen to sulfur and to selenium, modify the ring system and get mobilities? And also this work was published in Macromolecules, which showed good mobilities for these materials. So we come back to the aspect of having this to be direct aligned, or direct alignment as the project title was. So the idea was to put fluorinated parts on these systems, having a thiazole, having the thiophene, and having different groups. So Maciej managed to make about 15 different compounds. So again, pharmaceutical companies would love things like this. So we made 15 different compounds, and basically we managed to make different 15 structures or even X-ray structures of these compounds in terms of showing their analysis and showing their thing. And it was obviously published in recently, most recently in Organic Chemistry Frontiers. While the paper was out, we got approached by some people in Japan for the materials. They said that we're interested in the materials that you're making, and could we use them for biological materials? So currently we are in talks with them to see how we can push forward in terms of them taking our materials. So as I said, biomedical applications for these fluorinated stuff containing the thiazole has attracted attention because it's involved in biology. We could also, apparently we use it for batteries and also other polymers, and obviously the famous one, Kevlar as well. What has been the impact of this project? So we've demonstrated that we could have a fundamental science toolkit to integrate into bioelectronics. We have managed to have intellectual property on this project for the US and in Europe as well. So we have intellectual property on these materials as well. We've managed to publish 5 high impact journal publications. Not only they're high impact, but they've been selected to be on their front cover. The postdocs, the researchers, Maciej himself won an award by presenting some of the research that we did in Spain in one of the top international material conferences. One of the graduate students that was working on the project, Dusulu, was selected basically to get an award as a postdoctoral research fellowship. So after her graduate program fellowship ended, she applied for a postdoctoral fellowship, and I had to write a support letter, and it got accepted, and now she's a postdoc at one of the American universities in the States. So what's the future with this? We've utilized nature-inspired materials to derive what we want for plastic electronics. So the idea is, if we could get more funding, can we use fruit-inspired? To my surprise, I love blueberries. To my surprise, blueberries conjugated material. As I Googled it and I looked at the structure, it's quite conjugated. People might tell me, but it's quite expensive. But we're not talking about the fruit itself. Some fruits go off later on. Can we utilize the rotten fruit and use the same materials where we could extend it to the plastic electronics? I spoke briefly and I mentioned that the important field coming up is about electronic skin. Electronic skin is a big field. I can't say a big field, it's a huge growing emerging technology that's been in the last year, and not many people are working on it. We could use it for medical application, and this is all centered on the conjugated polymers that we are looking into, and hopefully we could get some funding to initiate this in Qatar. So last but not least, I would like to finish by saying that no matter what the future will be like, one thing is for certain, we will need some type of energy, okay, to power that future. And where does that energy come from? It should be obvious. It's always been out there, and we should utilize it to our best ability. Last but not least, I would like to thank Qatar Foundation for the great support, QNRF in particular for supporting the project. I would like to thank Li Fang and Jingsu Kim for this project. Other collaborators that have also worked with us. You can see some of the students that work in the group. This is Mache over here. These are all students. The first row of students also participated in some of these projects. They're undergraduates. Some of them are going to do PhD. Later on, some of them have been awarded for the Junior Research Fellowship. And others at the back here, the students, undergraduates that are joining and are interested, hopefully will be doing other research. Texas A&M, US, Michigan University, and all the other collaborators. And last but not least, I would like to thank you, and I'll take any questions. Thank you.
Thank you so much, Dr. Hashemi. It's a wonderful presentation. I have a question here. One of the main issues with organic and hybrid organic material, in addition to low mobility, is the stability. Any words about this major issue?
Yes, I mean, I don't know if the person that was asking the question saw, I had that in one of my slides, that stability is an issue. However, one thing that we have to remember, the organic hasn't been in the market as much as the silicon-based materials. Silicon-based materials have been in the market for 50 years. The organic has been in its 20 years, you could say. So stability, we are improving on the stability. I could say there are materials that are stable. Okay, whether they are competitive to the silicon, yeah, no, they're not, but they are improving. But the idea is we are increasing them. As I said, we started off with 1% 20 years ago. Now we're achieving 18%. So we're basically increasing the efficiency by 1% more or less. It's cheaper and it's flexible. So it gives us a wider range of applications than the silicon base, which is 25% maximum. And the stability also is what now people are thinking about at 10%, 10 years or so. Okay, so I mean, it is growing, but the stability, yes, is correct, it's an issue. But we are trying to work, myself and other people in the world are trying to work on the stability.
Thank you. Another question, what is the degree of freedom for bendability/flexibility of the thin films fabricated from these prepared materials, and for how many bending cycles can it sustain?
So the flexibility is a very cool. I mean, the biggest thing about these materials is their flexibility. As I demonstrated in one of the diagrams that I have, I mean, if we over here, if we can make these flexible enough that we could put them on roofs and stuff like that on stadiums, it is quite flexible. But in terms of the mechanical bend, how mechanically we can bend them, how many cycles they last for the particular materials that I've worked on, we haven't tested that. But we're obviously open to people to engage that would be interested to test these materials further. Again, at the early stages, our interest is, can it generate efficiency? Does it have good mobility? And obviously, we are willing to improve on these materials and work on it. As I said, interest from Japan was received, which is nice. Would like to get interest from people in Qatar to look into our materials. The issue that we have is we get interest from other people outside. We have to send the materials and we wait for a very long time to get the results back. But if we get interest from people in Qatar industry, we're more than happy to provide them our materials if they are interested.
Thank you. So you touched upon the Qatar context. I want you to elaborate more on that. Plastic electronics, organic electronics within the Qatar context. Which sector can benefit from this technology?
As I collaborate a lot with Total and Shell, and I'm hoping they're listening here as well. So a lot of companies here can benefit. As I said, plastic electronics is not just for certain companies. The medical companies, the medical field could also relate. As I said, one of the biggest things now that's emerging technology is the electronic skin. What do I mean by electronic skin? So we have these conjugated materials that are quite flexible. So imagine yourself, you put these flexible materials on your hands. You're sitting on a beach, right? And then suddenly you're exposing yourself to too much radiation. You need to know, wow, this electric material which is on your skin will basically trigger something. It gives you a point that you've exposed yourself too much, go and put some sun lotion. Alternatively, people that have diabetes, right? We have to measure our blood glucose level every day. Imagine you have a sensor on your arm or on your finger, as I showed in one of the videos, that will tell you your blood glucose level is this much. You need to inject this much insulin. So it's a huge field, and all this utilizes the plastic electronics, the material, the conjugated materials that we make. So going from Total to Shell, the companies that I work with, and I said Total and Shell, not in Qatar, but in France, in the UK, in Japan, they utilize these materials heavily, and they've got sections where they do research. So we're hoping that more companies in Qatar also will be interested by knowing what research. But unfortunately, the companies will straight away come and tell you what TRL level is this. Ideally, remember, we're in TRL level 2 to 3. If we get the help of companies, they could obviously push this further, and that's what we're hoping.
Thank you so much. Thank you. I'll move on to our next speaker now. I think by now the audience will appreciate the diversity in the topics that we are discussing today. So we went from aluminum composites, and then we went to bioengineering, and then plastic electronics, and now we are back to something that's closer to the oil and gas industry. Professor Bilal Mansoor, Associate Professor from Texas A&M at Qatar. His project title is Multi-Scale Modeling and Characterization of Advanced Interface Materials for High Energy and Corrosive Environments. Dr. Bilal Mansoor is an Associate Professor in Mechanical Engineering Program. He is the Director of Engineered Materials Manufacturing Lab and Corrosion and Reliability Lab at TomQ. His research focuses on developing structure-property relationship in novel metallic systems designed for extreme environment use by deploying various multi-scale characterization tools from the macro down to the nanoscale. He is currently leading several QNRF and industry-sponsored research initiatives of vital importance for the state of Qatar. Some of his continuing research initiatives with Qatar-based collaborations include development of biodegradable magnesium alloy orthopedic implants, development of new tools for oxygen sensitivity assessment of materials with Qatar Shell, and additive manufacturing of intelligent parts for potential applications in energy and medical sectors. So please let me welcome Professor Bilal Mansoor. You are muted, Dr. Bilal.
I'm sorry.
Yeah.
Thank you, Dr. Barkalan, for the introduction. I thoroughly enjoyed the talks by all the speakers. So let me share my screen, and please let me know if you're able to see it properly, and then I will be. Let's see. I think I'm on the monitor. I hope it's clear now.
Yeah.
Are we good? All right.
Yes.
All right. So again, I'll thank you, the QNRF team, for inviting me. I know most of the speakers here know these topics and hold these topics dear and near to their hearts. So what I'll try to do is I'll talk a little bit about this one particular project, which we did conclude about a year ago, a little over a year ago. It was part of the Cycle 7 and had to do with taking some of the novel interface materials. I'll introduce you to the interface materials just in a little bit. And we wanted to see if we can apply some of these new materials in high energy and corrosive environments. Again, a term of art, so I'll explain that in a little bit as well. I think Dr. Barkalan has already introduced me, but just to plug in, I lead the Engineered Materials and Manufacturing Lab at the Texas A&M University at Qatar. I am also involved with the corrosion and the reliability lab here and on our main campus. One disclaimer, where I'm located at the moment, there is a bit of construction work around and I don't have control over it. So if you hear the banging noise, that is not the applause from the audience, but it is basically you hearing the drill work going on. Again, I apologize for that in advance. All right, so what I want to do is I want to just give you an idea of what the project was. Basically, we wanted to see if we can deposit some nanoscale composite materials to protect the strategic oil and gas industry assets. And can we do that at extreme environments? You know, the Qatar oil and gas industry, unlike other industries, faces a lot more intense environments, not just in the day-to-day equipments, but also in some of the more strategic equipments. An example of that would be the installations and the strategic assets at the GTL plant that Qatar Shell has. And these are some of the applications that we wanted to see if we can target with these new nanoscale composites. So we really had three objectives in our mind. We wanted to design a metallic ceramic composite system, and we wanted to achieve not just the mechanical properties, but also can we do that without compromising the resistance to corrosion. And in order to do that in a more efficient way, instead of the high throughput experimental approach that you'll typically see, we wanted to see if we can develop some multi-scale modeling tools and bridge the gap between what you would see in a microscale modeling of materials and link that to the mesoscale. Another new aspect of this project was that we wanted to deploy some of the molecular dynamics based models, and we wanted to capture that by way of some finite element codes as well. So this was a complete multi-scale approach to solving this problem, and this is sort of captured here in this framework. The mesoscale crystal plasticity tools, taking into account some of the viscoplasticity that you'll expect in the metal systems, and then some of the continuum dislocation dynamics type work. Here, the talk is mainly going to be about the implementation of that work, which relied a lot on the modeling that was done by our collaborators. The experimental work that we took over had to do with characterizing the materials that were produced, and seeing if we could inform some of the models and better design these and test for the applications that we had in mind, i.e. the oil and gas industry applications. So this was the overall framework for the project. The team, I'm just going to skip through it quickly to show you what the team looked like. Of course, there was Texas A&M main campus and Qatar involved. I was leading the project. We had Dr. George Ayub, who was basically carrying out the day-to-day tasks of this project. And he's now a faculty member at the University of Michigan. We had Dr. Wei Yang. She was a postdoc who was mainly responsible for the modeling aspects of this project. She's now a professor at the Shanghai University. Then we had Dr. Ali Asman that joined the team in the last year of this project, and he mainly worked on characterizing some of the materials that were produced from a corrosion standpoint, and also looking at their mechanical properties. He is now at the Qatar Environment and Energy Institute, and he also jointly works with Texas A&M University at Qatar. The international team obviously had participation from the US. We had collaborators from Washington State University, Professor Hussein Zubib. Those of you who do not know, he just recently passed away after a roadside accident about 6 months ago or so. So he was the major driver for this work. He's a big name in the computational world, and has been a mentor to not just me, but the rest of the team, as you could see, and was instrumental in allowing some of these young folks that you see on the collaborator list to make it to faculty members at these prestigious universities. We also had Dr. David Field. He was mainly responsible for making the materials, and he was assisted by his PhD student, Tarang Mangol, who spent quite a significant amount of time in Qatar at Texas A&M University at Qatar. And now he's a postdoc researcher at the PNNL labs at the US. So overall, I think in terms of the human side of things, we were able to not just achieve the project's goals, but also were able to advance the human capital both in Qatar and also in the US. What I want to do was I just flipped the way the order of the talk was. So I want to just tell you what the output of the project was, because I think that's the research outcomes seminar. So in that spirit, I start off by showing you what the range of publications were when it came to this project. As you can see, I have about 9 projects, 9 publications listed here. They're all in different journals. You'd see a lot of material science and engineering focus, but then there is computational material science journals all the way down to applied physics, and then to Scripta Mat, which basically is a format for quick publication. So you can guess the amount of output that was generated by way of this 3-year project, and it dealt with all aspects of material science and engineering. There is an applied component to the talk. There is an applied component to the research. There is a computational part to the project, and obviously there's a lot more science that came out of this project as well. And beyond these outputs in the form of publications, you could see that some of these outputs were locally communicated as well, which I believe is very important, and the keynote speaker pointed that out as well, to not only disseminate information in international conferences and events, but to be able to drive this discussion between industry and academia. We started by our yearly material science and engineering symposium, where I believe Dr. Parkalan has been involved. Also, some of the other members that you've heard from have been regular speakers. This is a joint collaboration between Texas A&M University at Qatar and Qatar University, and this event happens yearly, and we basically take turns in terms of hosting it. And the focus has always been material science and engineering. Another important output that came was this material selection, reliability, and corrosion workshop that we did back in 2018 towards the culmination of this project. Basically, the idea was to assemble the research depth that we have in Qatar, both from academia and industry, and to some degree from the ministries, to see if we can have a better take at what are some of the important challenges. This was mainly focused towards the energy sector, and a lot of interaction has happened in terms of taking our students and researchers to visit the local industry. This is a picture taken at the Qatar Shell Research Technology Center, where you could see that the students from Texas A&M were involved. And again, they were exposed firsthand to what the industry desires. Engineers who don't only understand science, but can also take on some of the more pressing engineering challenges. So these are some of the outputs, but most importantly, the output that makes me proud is this image that you're seeing on your screen now. This was the runners-up best representative image of an outcome back in 2018. What you're seeing here are titanium nitride dislocation, nucleation event, and it's a combination here. These are titanium layers, and then you're seeing a dislocation popping in under compression. Now, normally when we think about composites, or let's say ceramic materials, we don't tend to think in terms of dislocations being generated without cracking. But here, by way of these molecular dynamics simulations, a lot of the work came out of Dr. Ayub's efforts. We clearly demonstrated that there is a way for us to have dislocation nucleation inside ceramics without coatings. So hang on to this thought, because this is important, because this is something that's going to link to our design of these nanolaminate structures, which goes to the heart of the problem that we were trying to address. So the outputs, as I've shown you, were significant. I believe that the new science and the applied sense, the experiment techniques and the modeling techniques that came out were successful in tackling some parts of these fundamental questions, which had to do with, can we engineer a nanolaminate? I'll explain what that is. And can it basically perform under extreme service environments? So those of you, who are in the audience, not the panel that we have, corrosion tends to happen when you expose a metal to the environment. And the simplest way by which we can stop this degradation of a metallic surface is to take a barrier and put it on top of the metallic surface, kind of like disconnection between the substrate here and the environment. If you don't do that, you would have corrosion. If you can do that, it will reduce some of the corrosion. And if you do that efficiently, you can reduce some of the costs. So here, basically, I've just pulled this statistic off of the internet. US alone spends about $300 billion annually on corrosion. So imagine if we can have materials that can be applied to critical assets that can help us not just create this disconnect and provide the corrosion protection we need, but also provide us some of the materials mechanical properties, then that's a win-win solution. And that's what we were after. So thin films or nanolaminates are not something that are not applied in the industry at the moment. These are already some of the solutions that exist, but mainly the solution that you'll typically see in a range of different industries has to do with monolithic systems or nanolaminates, which are primarily transition metal nitrides. So you can see the range of industries that can be impacted if we can develop a solution of nanolaminates or thin films that can not only provide us corrosion protection, but also enhance some of the requirements of mechanical properties. So things like microelectronics, down to jewelry, to your glasses, to more cutting tools and corrosion protection in more critical assets. All of these can be addressed if we can create these nanolaminates. How are they different? What is the challenge? If you look at this plot here, you'd notice that the ceramic materials lie here. They're very strong, so that's great, but they tend to have a lot limited ductility. That's where the compromise comes. You can apply them as a coating on a material and save the substrate, but the problem is they tend to break. When they break, they open up and they basically break that barrier that you want to create with the environment. So how can we address that? Basically, if you look at the literature, you would notice that nanolaminates are not something new. The people have been going at it for a while. This is a picture back from 2001. Here you see copper and niobium layers that have been deposited on a substrate. And these are all about 20 nanometers thick each. And the outcome of applying these type of coatings and then stacking them up to make a more fundamental material is that you can achieve high strength. If you have copper niobium combination, you can get strengths of up to 2 gigapascals, which is very strong. It's almost close to the theoretical strength that you can achieve in these kind of metals. Or you could do copper nickels and you can get strengths close to about 1.6 GPa. So mechanical properties certainly can be improved, and metals tend to have a lot of ductility, so that addresses some of the problems that we've seen in the thin films. And they give you all sorts of advantages: fatigue resistance, radioactive resistance. However, the problem is corrosion. If you're going to use it in oil and gas industry, if you put a copper niobium together or a bimetallic couple, that's a recipe for disaster. You will have galvanic corrosion. You cannot do that. So the answer to these two fundamental problems, can we have high strength and can we have adequate corrosion response, begs that you use ceramic materials in some shape. Here is an example that is about 10 years old now, where you can see titanium nitride, and it's basically alternately deposited with aluminum oxide, both ceramic materials. And in this case, of course, you can achieve high strength because ceramics tend to be strong, but there is again problems with ductility. So you can apply it, but the thing would break. Of course, it offers better corrosion resistance because ceramics tend to be a lot more stable when it comes to interaction with the environment. So how do we address both if we can combine the ceramic materials and metals in the form of nanolaminates? And that's what we wanted to try. And the challenges we wanted to address were, can we look at some of the corrosion kinetics and then put them in environments which are more suitable or which are more representative of what happens inside, let's say, an oil and gas reactor. And can we do that without compromising the mechanical properties? So the part that had to do with thin films and corrosion resistance, the concept has been tried. If you look at the data that's published in literature, you would notice that all the way from 1990s, people have been trying titanium nitrides, titaniums with different kinds of combinations, and they've had some success. However, when it comes to ceramic inner layers, the fundamental question is how thick you want the ceramic to be, how thick you want the metal in combination with the ceramic to be, and is there a technique out there that can do that fast enough and without defects? So this is where first part of the project comes in. These are some thin films that were fabricated in Washington State University, basically by magnetron sputtering. Then some RF sputtering was carried out for the nitrides. And we also tried some DC sputtering. So we had different ideas in mind. We also applied some deformation-based methodologies to create these coatings or create these nanolaminates. Here, what you see is a TEM image that was taken here in Qatar. You can see a titanium layer, which is about 4.2 nanometers, and then a titanium nitride layer, which is about 60 nanometers. So we're able to achieve these alternating layers, but the question was, can we control it? Another thing, if you look at these glancing angles, you can sort of confirm that these are indeed titaniums and titanium nitride, so we had some confidence. So one part of the project was the materials fabrication, and I'm happy to report that by the year 3 we were able to successfully produce a lot of thin films with good control over the periods, and that allowed us to do our study, which I'm going to talk about just in a little bit. This is what an SEM image basically shows the alternating layers, and you can notice how we can control the periods and the thicknesses involved. Based on these successes that we had early in the project, we were able to create a short study, which was carried out in Qatar. We took 5 different materials. We started with a titanium nitride, which was about 90 nanometers, then had a counter to that with a very thick nitride system, and then a combination of thin inner layer of metal and a thick inner layer of metal. So please keep this in mind. It will make life easy when I show you some of the other results. Now, I must confess that while we were working on this project, the processing was still being evolved. As you can see, some of these pores are visible. So the corrosion response that we were able to achieve was with these defects in mind. And that basically would qualify some of the conclusions that I'm going to make. If you look at the mechanical properties of these nanolaminates, here what I show you is pure titanium nitride that was about 1300 nanometers and pure titanium. Reasonable hardnesses were achieved, and as you can see, the titanium nitride tends to be about 8 gigapascals or so if you go for the reduced modulus. Combination of these would obviously depend on where you measure the hardness, but this was good to know that we are able to produce the nanolaminates by the sputtering techniques, but we have hardnesses which are comparable to at least the bulk materials, and that is also representative of if there are any defects. Now, so in year 3, we wanted to look at some of the corrosion response of these materials, and as you can see, if you look at the different combinations, you would notice that the behavior for the titanium nitride with the inner layer tends to be far superior, and we had a hunch that it had to do with how much blockage the thin titanium layer was offering, or the thick titanium layer, the inch layer was offering. So we went ahead and did some electrochemistry studies on these materials, and again you would notice that initially we could see that the response for the inner layer that was thick was superior by 1,000% when it comes to corrosion protection, and these are about 16 hours. And when we extended this study and we continued for about 32 hours or so, you could start to see that the titanium nitride and the interlayer differences become a lot more comparable. However, again, with the caveat that there were some defects that we saw in our material. And I can see Dr. Parkalan on board, so it probably means that
you have a couple of minutes here.
Which is fine. I think I'm on time. So bottom line is that the significant decrease in the resistance that you would see with these nanolaminates when you have an interlayer is basically the period of immersion. So we were able to at least get the sense of how our nanolaminates would behave if we were to put them in a more energy-intensive environment. A lot of work was done on characterizing these materials at higher temperatures for creep response. This is a very involved study which requires specialized tools. A lot of them were not available initially in Qatar, so we relied heavily on Washington State University, but thanks to Curie now, a lot of these electron microscopy systems are available, and that allowed us to make a lot of quick progress. Again, the result here shows that the inner layer material still behaves a lot nobler. The overall process that we were able to uncover was that the pinholes and defects that exist when you deposit these materials, they're really the controlling factor. If you're able to deposit a solid layer of metal on top of whatever substrate you have, you can have a better response. But this goes and begs the question: if the substrate is not a nobler material, you'll run into galvanic corrosion issues. So that's where we were. I think I want to acknowledge QNRF for providing the support. I also want to capture the international nature of the work that was carried out and all the students that were involved. You see here Parker West, he visited us from main campus. Anna initially worked on this project and then is now about to finish her PhD. Mustafa is now a PhD student at University of Michigan, and Jahanzeb, who also graduated, is now at Intel, and he's working as a process engineer. So with that, I'll conclude. If there are any questions, I'm happy to answer. I'm sorry that this was a more overview-ish presentation, but I guess I wanted to capture the outcomes that were produced. Thank you.
Thank you so much, Dr. Bilal. It was really informative. There's a couple of questions here, like more like comment. I think I can tie it up with my own question. So when you talk about extreme operating conditions, you're talking about ranges of temperatures, pressures, carbon dioxide, hydrogen sulfide. Out of all these factors, what do you think is the most critical in Qatar context of extreme conditions?
So in terms of extreme conditions, if you're talking downstream, when you come to processing of the oil and gas, you're talking about high temperatures, mostly high temperatures. A lot of it has to do with high pressures as well. So for example, Qatar shell, usually the temperatures that are in some of the steam methane reformers can be close to 1,000 degrees. Even if you go further downstream, you can have heaters that are operating around 300 C or so, and a lot of pressure is also there. So temperature and pressure downstream. If you're talking upstream, certainly the gas in the environment, it tends to be a little sour. Carbon dioxide is certainly there. So there are two different spectrums. If you're mainly concerned with downstream, it's more temperature and pressure. If you're talking upstream, it's all the corrosive gases along with some temperature, sure, but not that high. Yeah.
Okay. I think we are running out of time, so I will move on to our next speaker. There's a couple of comments here. I think you can read it later. Thank you so much, Dr. Bilal. Thank you for your presentation. Let me go to the next speaker. This is our final speaker. And after this speaker, I will have a couple of minutes of closing remarks. So I would appreciate if all the attendees can stay till the end so that we can tie up all the things that we have discussed today, and we can close the meeting after that. So our next speaker is Dr. Fadwa, a senior scientist from Kiri Energy Center. Her project title is CRAN Kiri Initiative for Solar Energy Harvesting Materials. Dr. Fadwa joined Kiri in March 2014 as senior scientist. She is currently a member of the Energy Center. She is program research director of Novel Material for Energy, specialized in using computers to understand and design materials for different applications prior to their synthesis in laboratory settings. She received her PhD in physics from Montreal, Canada. Dr. Fadwa has more than 15 years of experience in computational material science and nanotechnology. She has expertise in applying both atomistic and electronic structure calculations and statistical machine learning to material science within a high-performance computing environment. Fadwa has published tens of highly cited peer-reviewed journal papers. She holds a number of international patents and invention disclosures in the area of novel materials design. She has received several distinguished national and international awards and research grants. She is engaged within the computational community in Qatar and internationally through conference organizations, student advising, and science outreach. So please let me welcome Dr. Fadwa.
Thank you, Dr. Bara, and thank you for the invitation. So, last but not least, so I'm the last speaker. So I would like to actually to thank you for the invitation, and I would like also to I will be very brief, hopefully. I will tell you a little bit about the outcomes of our project, which is titled Crack Solar: Design of Non-Toxic and Stable Hybrid Materials for Photovoltaics. So the work was done in collaboration with between Kiri and Trinity College Dublin. So this is the team. So I started with the team. So in the team we had from Kiri, Dr. Nuar Tabit and Dr. Fahad Harbi, who have left for other assignments like in last year or so. And then Professor Stefano Sanvito and Valeria Nicolosi. And we had 3 talented and bright postdocs that were working with us, Hiso, Atayib, Annan, and also 2 graduate students at Trinity College that one of them graduated and one of them is defending her thesis. So let me move to the next. So actually, I mean, the previous talks made my life easier. So especially the talk from Dr. Mohammed Hashimi. So I mean, as you might guess, this project is interested by designing materials for emerging and devices for emerging solar cell efficiencies. And those who know a little bit about solar cells must be familiar with this chart that simply, I mean, shows the historical evolution of different technologies. And here it zooms mainly on emerging PV technologies, so such as the synthesized solar cells, perovskite solar cells, and so on and so forth. And then we can see how they have evolved. So One of the technology actually that have attracted lots of attention in the past 6 years or so is the hybrid perovskite technology, and you can see it by this line here. So you can see that since 2012, I mean, it has increased in a very, very significant way. Not only, I mean, as monolithic solar cells, so where the absorber is mainly made from those materials that are easy to synthesize, that are chemically synthesized and so on. They are very tolerant to defects and so on, but also in combination with the silicon solar, more conventional as tandem solar cell. And you can see that the emergence of this material by themselves, I mean, the efficiencies keep increasing. And on the other hand, once in junction with the conventional silicon solar cells, they're also actually making the efficiencies surging. So the record is 29.1 when perovskite with silicon is used, and perovskite alone is 25.2%. So the main scope of the project was really to, first of all, try to optimize the light absorbers, so in these emerging technologies. And in that aspect, we focused on two classes of materials: the perovskite materials that I'm designing here by PS, and then the 2D materials like molybdenum disulfide, for example, that I'm showing here. And then in this collaborative work, actually, we wanted to try to solve some challenges that are in these materials. I will talk about them very, very quickly. So by creating and by using computational approach to create material databases for both perovskites and 2D materials, to screen those materials, to look at their properties, and to try to find the best materials. And then, as you can see, so I mean, we go towards theory refinement. I will talk about that in a little while. And also, if materials are promising, we go to the lab synthesis of the thin films, and then to the characterization, and then to the device. So to be able to do that, actually, we had to use a multi-scale approach, where we started from really very the beginning, the electronic state, and then we calculated the phonon properties, the carrier properties, and so on. All these are ingredients actually to be able to simulate the power conversion efficiency of those materials. And then based on those predictions, we made decisions on whether some of those materials could be synthesized or could be promising for solar cell application. So, and then you can see some SEM images here about the lab validation and testing. So what is computational materials design? So it often uses density functional theory, or so-called DFT calculations, where we start from the periodic table of elements, and we use certain formalisms, so within the DFT and approximations and so on. And we often actually, to optimize the loads and so on, use supercomputers for that task. And then in this case, so in the case of our scope, where we wanted to design efficient and stable and low cost and also environmentally friendly solar cell materials, then in that case, actually, we start simply from input structures, so different crystal structures with different compositions. And then, what we do is that we obtain the results from density functional theory, we process them, and also what we do is that we relate that to the optical properties, which are really the very first and important parameter that is needed for this class of material, because we're looking for materials that absorb the sunlight. So using this approach, actually, we go back to our screening. We can actually have a very rough estimate of the power conversion efficiency. If a material falls within the range that is of interest for us, we keep it and then we process it further. And if materials do not fulfill that basic requirement, they are discarded, and we keep them for other type of application, and we store them in our database. So I will be presenting very quickly, two types of investigations that we have undertaken. So the first type really is driven by questions raised by the experiments, where we do the computation, and then we come up with some theories, and also we help actually the experiment for interpreting their findings. And on the other tab, which is a little bit more new actually and emerging, is that we start from computation. We propose materials for experiments. We validate them in laboratory setting, and then we keep actually improving the materials until we get the properties that we are interested in. So the first thing that I wanted to mention, I mean, in the previous talk, I mean, you mentioned actually about the stability, and indeed, actually, even the hybrid perovskite materials actually suffer from issue related to stability, because I mean, these are materials that are grown from solution processing. They are grown at like low temperature and so on. So they are really very prone actually to decompose under different conditions such as humidity, ultraviolet and oxygen, and so on and so forth. And then on the other hand, there is another issue, is that these materials, as you see them, so if you take this methylammonium lead iodide, it contains lead, which is a lot of people actually are raising this issue that lead might be toxic. So then we took this challenge, and then we looked at these two major aspects actually that are really putting the technology at risk to be deployed at larger scale. Okay, so and then what we did is that we started to look at different actually modifications in the materials composition in such a way that we can actually screen for stable and non-toxic material. So in some cases, I mean, we took, for example, hybrid perovskite halides, and we tried actually to improve their stability. But on the other hand, I mean, we looked at other classes of materials that are lead-free, like the vanadate and also niobate and so on and so forth. So very quickly, so you know, out of our investigations, I mean, out of 3,000 candidates we looked at the time, we came up with 12 candidates. Some of them, you know, turned out to be never actually synthesized in the past, and then well, we have disclosed them to the IPTT for invention disclosure. And then in some others, actually, we brought some new concepts actually to improve the band gaps and the properties, and this has been also filed. And then you can see that, you know, we have done some attempts actually to synthesize these materials, which is in this case the cesium niobium oxysulfides. And then efforts, I mean, it's are still going on, because you know it's not easy to optimize the condition, especially when we are talking about a new material. Now let's move to the next. So the other challenge that is facing this technology is that you see, I mean, this is here I'm showing some solar cells, and you see that the cation that is sitting in the middle, which is an organic cation. So if we change it, actually, we can modulate the optical property, and also if we change the halide, we can also change the optical property, or the color and everything, the efficiency and everything. So this leaves us really with a huge actually space of possible combinations. And then you can see this is again, I mean, the power conversion efficiency chart as function of the years, and then you can see that, you know, the community has moved from simple chemically processed MAPI, okay, material, to a mixture of several, you know, cations and anions to be able actually to reach higher efficiencies, and to be able to reach also the desired stability. It's more the stability that is an issue than the efficiency, to be honest. So then, I mean, what we did is that, okay, we started to do some high throughput DFT calculations, and then we quickly realized that, you know, by looking at the structure of those materials, by looking at the lead family and also the vanadate family, we quickly realized that it's going to be very, very challenging actually to analyze the data and come up with answers actually to our question regarding to the stability in particular. And in that aspect, we called for the help of our colleagues from our sister institute. So I will be adding actually people incrementally that have actually contributed to this work. So we called for the team of Dr. Halima and Raghvendra Mall from QCRI, and then that was our first actually work of using using machine learning applied to DFT data to be able to do some clustering on the perovskites, and also to look at their properties and their structural properties, and to be able to see which perovskites can be mixed together. And then we took it further, so it was such a success actually that we moved from very simple cation to actually larger cation and organic cation, which was also a challenge. And then we built a database of all these calculations that you see here. So this has resulted into thousands of the DFT calculations, so both in halide perovskite and chalcogenate perovskite. And then you can see here, so here I'm displaying the graph that is showing, I mean, the distortion of the octahedral deformation, or the octahedra that are composing the perovskites. And this correlates very, very tightly actually with their intrinsic stability. In fact, I mean, what I want to emphasize is that these perovskites are often degrade very quickly because they are intrinsically not stable. Okay, they're in a metastable state, and this is why, I mean, when we mix this cation and ions, we bring them actually closer to their stable position. And then in that case, actually, we called again for the help of machine learning to try to derive some trends, to try to see what are the most important features that are governing this type of deformation and so on, especially the impact of the cation. So we know that the cation actually is the best way actually to tune the stability of those materials without altering their optical properties in significant way. And then what I want to show you is that, I mean, we came up with a machine learning model. You can see the results of the machine learning model. This is the 2D demonstration of this machine learning model. And what it helps us actually to estimate the stability of a given composition. So in this case, these are lead iodide and these are lead bromides. So it helps us to define the stability of certain composition as function of the radius of the cation. So each of those cations that you see here is moving from smaller to larger cations. Okay, and then you can see that with this model, actually, we can identify the stability regions for this given composition, and we can even find actually the optimal cation radius that could stabilize better these materials. And this here I'm showing the three-dimensional phase diagram. So we have taken the case of lead-free, and these are some well-known lead-based iodide, and the green dots that you can see here are some experimentally reported materials that have been already synthesized. And you can see from this graph that, you know, the black region corresponds to stable materials, while, I mean, the yellow region or white region is unstable. So this type of diagrams actually is very, very useful, because you can imagine how much, you know, compositional space we are able to sample without having to do the experiments and try by trial and error and try things, I mean, over and over. Then I would like to highlight actually the team actually that helped us actually to take that demonstration to the laboratory. So it was by the Dr. Abdelhaq Belaidi, and then Adnan Ali, who is postdoc in the project. And then what we did is that, okay, we said, okay, let's use our machine learning model predictions to narrow actually the search, and to be able to synthesize some stable triple cation perovskite. So in this case, we are mixing 3 cations that you can see here, and here, I mean, you can see the change in color when you change, for example, 2 cations and you're moving in this direction. Helped with like characterization and imaging and so on, and I would like to thank the Curie Core Lab facilities for offering this support. I mean, we actually came up with a very good understanding of, you know, what is going on, and validation as well for our machine learning model predictions for this specific composition. To move ahead, I just, want just to touch base what the team in Trinity. So if you remember, the team at Trinity was specialized in looking at the other class of material, which is the 2D materials, heterostructures. So instead of looking at, molybdenum disulfide and so on, so there was actually an interest and also to look at heterostructures. But the problem is that, if you combine two decalcogenide materials with each other and you do some optical spectroscopy, you cannot detect the contribution. Where is the contribution coming from? So then, what Anais did in her work, actually, she modeled using this functional theory a number of monolayers and bilayers of metal chalcogenide materials, and then she has been able actually to extract some trends and so on and so forth. And then the question that we raised is that, could we actually build a model that would help us to predict the properties of heterostructures or bilayers without actually having to do the explicit calculation, which is often very expensive? And that was really the idea of her work. So when she visited actually us in I think it was January 2019, I think, if I'm not mistaken, she worked actually with us in trying actually to look at the different properties and of their optical properties of these materials, and also to look at the methods on how she can cluster and find two materials that can better match with each other in terms of optical properties and so on, so who have a lot of similarities. Next, actually, I would like to highlight the work of Jenny. So Jenny was under the supervision of Valeria Nicolosi, she was coached by Noor and Fahad as well. And then she worked actually on trying to use exfoliated 2D materials actually for solar cell devices and testing. So Valeria Nicolosi's group is specialized in exfoliation of 2D material. And then she got a PhD student, so she got trained and so on to make devices and so on based on 2D materials. But then, there was a need to for a huge actually amount of optimization actually to be able to get working solar cells with molybdenum disulfide. It's normal. So as a mitigation strategy, to that, what we thought that, okay, why don't we actually try to use this decalcogenide materials in perovskites to enhance the device lifetime and efficiency. That was based actually on previous publications that used other type of materials like C60 and so on to be able to enhance the whole transport, protect the rapid degradation of the perovskites, and also that is induced by the whole transport material. And in that aspect, Jenny came to Qatar. She stayed in Qatar at least 3 months. In her second trip, she was tightly working with Annan and Dr. Beladi, and then she actually managed to generate very, very, very interesting results in using molybdenum sulfide buffer layer for the synthesis of these materials. I will not. Yeah. So I need just 2 minutes.
Yeah. Sure.
Yeah. So that was my last actually. I wanted actually to anchor, and to show the contribution of each of the students, the postdocs, and so on in this project. But also what I have brought here, since I'm the last one to speak. So I wanted actually to show how such a project, in which landscape such a project has been maturing, over the years. So the seeding in terms of preliminary results and so on and so forth started in Kiri in 2014, actually, right after I joined Kiri. So I'm very thankful to the support. And then with Trinity College, and we applied for Qatar National Research Fund, where we got funded. But then you can see that the project has evolved and flourished really as the investments in research at HBKU and Qatar Foundation have evolved. So this includes, for example, the RAD supercomputer, and then the second generation, which is the RAD 2 supercomputer, and so on and so forth. Now we have evolved to a growing landscape of collaboration that that is from people that are really very interested to use these methodologies to other type of problems, especially that we have fully automated our processes. We are using machine learning methods, and we are even combining device modeling with the lab realization and so on and so forth. And finally, one of the outcomes actually of marketable outcomes, I mean, as you might guess, I mean, the target from the beginning was to get some databases, but we want a little bit beyond. And then we have created the Qatar Materials database, which is a local database that contains very unique data that we actually obtained from these automated workflows, and that we have been using in machine learning and to train machine learning models. And then as outcomes, I mean, we can have, and we have actually some commercially valuable products to the end users, like this perovskite predictor and this perovskite bandgap predictor that we have disclosed to the IPTT. Final slide. So in terms of general outcomes, so this paper have, this project have resulted in more than 20 scientific publications, 20 invited and contributed conference and presentations and prizes, journal covers, I mean, you can see them here, media and outreach coverage as well. And we have disclosed 7 IPs, 2 of them are patents and the others are more copyright and trademark and so on. We have 1 database, and we have also we have been building a human capital. But most importantly, what I want to emphasize is that this project have opened also more funding opportunities in other areas than just the solar cell industry, and a growing network of national and international collaboration. And with that, I would like to acknowledge again Qatar National Research Fund, Kiri, for very strong support from its management at all stages that you have seen, and also my colleague who actually have also helped with this work, and and so on. And finally, I would like to emphasize the role of the HBKU Sponsor Research Office. Without them, we cannot actually manage those grants, and also the computational resources from the research computing, Texas A&M, University of Qatar, imaging and spectroscopy and characterization from the Kiri Core Labs, and Trinity College Dublin Advanced Microscopy Facility. And I would like to thank you for your attention.
Thank you so much, Dr. Fadwa. That was a comprehensive presentation, and congratulations for all your outcomes, journal papers and conference papers, IP. Congratulations. There's one question here. You highlighted stability many times as your key parameter. Any value you may put on it, hours, days?
Okay. So, I mean, stability, I mean, if we are talking about stability in, you mean, okay, I get so the question is about whether actually those solar cells are stable for hours or days. No, I mean, we're talking about devices that we have nowadays and have been stabilized for more than 1 year. Okay, so there is significant improvement, I mean, compared to where the field was. Okay. So, and there are even now spin-off companies and also startups that are thinking about commercializing. But to be honest, where I see this perovskites really impactful is when they are used in tandem with silicon solar cells, so to enhance the efficiency.
Thank you. You talked, so one of the goals of the project is to generate a database for perovskites and 2D material for purpose of design and selection in optoelectronic devices. So how different is this database from existing database, and what are the advantage of the database that you generated?
Okay, thank you. This is very, very excellent question. So yes, we are aware actually of several databases available in, but many of them actually use either crystal structures that are very basic, so the basic crystal structure of materials, and the others, and on the other hand, the properties that you can extract from them are really very limited. So you don't always have access to the properties that you need. Okay, so in our particular case, so what we did is that we built a database that is based on large supple cells that are really very computationally expensive, where we explicitly actually mix the cations together. And when we do that, actually, we have access to information that is very, very valuable, that, you know, makes us really in the front in terms of predicting materials properties and the stability of these materials in particular.
Thank you. Thank you so much. With that, we have come to the end of the speakers. I have a small presentation, about 4 or 5 minutes. If you can, if the attendees can bear 5 more minutes. Thank you so much, Dr. Fadwa. Thank you.
Welcome.
Let me share my screen here. Okay, so I think my screen is visible now. What we saw now, all the speakers, we had 5 NPRP project speakers and keynote speaker. They all basically touched upon one of these materials. So I just thought I'll put a small table with the type of advanced materials and what are the current market drivers for this kind of materials. So we had people talking about electronic functional materials. So the current market drivers, I'm not going to read everything, it's on the screen. So energy efficiency, reducing cost, longer lifespan, higher power outputs. When it comes to bioengineering, biomaterials, textiles and hybrids, the compliance to regulation is very important. And then the drive to use recycled materials. So when you're talking about coatings and surface treatments, tightening regulations mandate cleaner, greener and less toxic products. So that is something to be kept in mind when working in these areas. And also durability, performance in harsh environments. So we already talked about the harsh environment in Qatar in terms of temperature, pressure, toxicity, chemicals, and all those sort. When it comes to materials for batteries and fuel cells, so reduce cost to access high volume markets, enhanced battery lifetime, recharge cycles, use of more readily available materials, metals and alloys. Enhance strength to weight ratio for transport and structural applications, cost efficient processes, reliability in demanding applications. So this, I think, this gives the overall picture of all the projects that we discussed today and the market drivers for implementing these research. I wanted to share this to try and encompass whatever we discussed today moving forward. So the key for materializing a brighter future is you need to plant, and QNRF is involved in these activities. So identifying the key area of investment and strengthening those creative networks between industry, universities and government. And you need to nurture them, obviously, growing the opportunities by implementing coordinated program of strategic investments in projects designed to enhance and sustain innovation. And when the time comes to harvest, you can harvest by reaping the rewards by systematically exploiting the commercial benefits. So the timeline for this, there were many questions on the chat window. Is it already implemented? Is it already manufactured? These are good questions, but we're still some time away from that. This is the blueprint that we have to follow. You have to first plant and nurture. And most of the projects you see today are in that phase, plant and nurturing phase. So we still have quite a time to go to the harvest phase, where you will see all these aluminum composites or bioengineering implants, plastic electronics, all the things that we discussed today. We shouldn't jump ourselves ahead, and this is a process. So the time to harvest will eventually come. I would like to share a couple of slides. This I took it from the NSF website, which talks about NSF's funding, which resulted, the funding that they've done for 30-40 years and then finally materialize into something useful. So you see the iPad there, and probably some of you are watching these presentations in an iPad. The iPad was generated due to 30 or 40 years of research leading into it. funded by a funding agency, just like QNRF does here. So you have microprocessors, you have LCD displays, you have lithium-ion batteries, all the speech processing devices. All this, if you see the highlighted, I have highlighted in yellow. 1960 microprocessor research was being done, and 1970 the internet research was being done, and then the GPS was done a long time ago. So all this culminated into what you see today as an iPad. So this shows, the virtue of patience, and also investing in basic research, applied research, and all research. So you never know where they lead into. So another good example is automotive applications. So you see several parts in this car, which are all due to research done over the past 2 or 3 or 4 decades even. So you see LCD monitors, lithium-ion batteries in 1990, catalytic converters, microprocessor again, car bumpers, remote car locks, and recently you have nanocomposites in these cars. And nanocomposite research was done in early 2000. So when you're doing this research, you don't have the idea where the application is going to be, but you're just trying to make breakthroughs and advance the science. So I just wanted to share these 2 slides just to give a big picture of what we talked today, and to tie up all our projects. We have reached the end of the seminar now. I would like to thank all the speakers for taking time and being very patient in delivering their lecture. And I would like to thank the audience. It's almost lunchtime. Unfortunately, we cannot provide you lunch today, but it's almost lunchtime, and thank you for sticking around. I want to thank the QNRF support staff for helping to put up this, especially Weil, who has been very patient in organizing rehearsals, and also today behind the scenes in making sure everything goes well. So thank you very much. Thank you once again, speakers. We will meet you again in the next edition of ROS very soon. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.
Bye.
Thank you, Barkalan. Thank you, everyone.
Thank you.